Hello there, and welcome to Physics with William, where curiosity gets comfortable and science is allowed to slow down a little. Tonight we're heading toward a question so small that it almost sounds unreasonable. What happens inside a quark? Not around it, not near it, not in the proton that contains it, or the atom that shelters that proton, or the matter that builds your hands, your chair, your ceiling, and the floor beneath you. No, we are asking something far more awkward and much more interesting. We're asking what happens inside one of the tiny ingredients that modern physics usually treats as one of the smallest things there is. Now that is already a suspicious sort of question, because quarks have a reputation for being the end of the line. In the standard picture of matter, they are not supposed to be little Russian dolls with smaller pieces tucked away inside. They are supposed to be elementary, which is a tidy scientific way of saying, as far as we can tell, they are not made of smaller bits. And yet, human beings are not very good at leaving a boundary alone once they find it. Show us a wall and we knock on it. Show us a locked drawer and we wonder what is inside. Tell us something is fundamental, and before long somebody is building a machine to ask whether that is really true or merely what we can say for now. So tonight we're going to sit with that question very gently. What happens inside a quark? It may turn out to be the wrong question, or at least the wrong shape of question. It may be like asking what is north of the North Pole, or what colour the number 7 wears to dinner. But sometimes the most useful thing in physics is not getting a quick answer. Sometimes it is learning why a question feels sensible at first and then becomes stranger the longer you hold it. Before we get into that, I would love to know where in the world you are listening from tonight, and what sort of hour it is in your little corner of the planet. Is it late and quiet? Is it early and dim? Are you under a blanket, on a train, at a desk pretending to do something productive while actually thinking about the interior life of quarks? Entirely understandable if so. There are certainly worse ways to spend an evening, and if you find this gentle ramble soothing or interesting, or simply a pleasant way to wind down while the universe gets increasingly unreasonable, I would be very grateful if you gave the video a like, maybe subscribed, and returned for more slow scientific wanderings. It helps this quiet little space reach other curious people who may also need a softer landing at the end of the day. Now then, let us begin not with quarks themselves, but with the very ordinary habit that leads us to ask about them. We live by opening things. That sounds almost childish when you say it out loud, but it is true. Open the cupboard, open the watch, open the seed pod, open the radio, open the question. Our species has spent a remarkable amount of time taking apart the world in the hope that its secrets will come loose in manageable pieces. It is a habit that starts early. Give a child a toy and before long there is a very good chance the toy will become a pile of parts. This is not always destruction in the dramatic sense. Often it is curiosity with poor planning. The child is not trying to ruin the object. The child is trying to see what the object is keeping to itself. Adults are broadly the same, only with better screwdrivers and larger funding proposals. That instinct carried us through the history of matter. People once thought substances were continuous, just stuff all the way down with no smallest pieces at all. Then came the atomic idea, and later the atom itself became a kind of breakthrough and a disappointment at the same time. It sounded final. The word itself suggested something uncuttable, yet it turned out the atom had structure. It was not the final brick of nature, but a busy little system with electrons outside and a compact nucleus in the middle. Then the nucleus itself was cracked open, conceptually first and experimentally later, and inside it we found protons and neutrons. For a while those two looked satisfyingly solid. Surely these were the compact kernels of physical existence. Surely this was as deep as the nesting dolls went. It was not. The proton and neutron, it turned out, were not indivisible either. Buried in them was evidence of something smaller, stranger, and in some ways less cooperative. Quarks entered the story as mathematical necessities before they became accepted physical entities. That alone should make us pause for a second. Sometimes nature does not show up first as a little object under a lamp. Sometimes it appears as a problem in a theory, a missing pattern, an awkward set of numbers that suddenly become neater if you imagine a new ingredient hiding underneath. Physics can be annoyingly like that. You're not always given the satisfaction of spotting the thing directly. Sometimes you infer it the way one infers a cat from the sound of something falling off a shelf in the next room. Quarks were like that for a while. Useful, elegant, suspiciously neat. And even once they became part of accepted physics, they refused to behave in the friendly manner we expect from ordinary objects. You can isolate an electron. You can isolate a proton under the right conditions. But quarks do not like being on their own. In fact, according to everything we have seen, they never appear alone in the world we can measure directly. They live bound together in larger particles, especially protons and neutrons, like tenants in an arrangement that no one can quite leave. If you try to pull one free, the energy you put in does not simply grant independence. It tends to create new particles instead. Nature, on this scale, behaves less like a child handing over a marble, and more like a magician replacing one impossibility with two. That already makes the question of what happens inside a quark a little slippery. We are dealing with something that cannot be picked up and placed neatly on a table for inspection. There is no tiny workbench where a physicist can set down a quark under a lamp and say, "Right then, hold still while I have a look inside you." The world of particle physics does not work by tiny tweezers and microscopic furniture. It works by collisions, traces, statistical patterns, energy sprays, and the long, sober business of interpreting what detectors tell us after something brief and violent has happened. And even before we arrive at those methods, we should notice something else. When we ask what happens inside a familiar object, we usually imagine that the object has an inside in the everyday sense. A watch has gears inside. A loaf of bread has a soft interior. A suitcase has socks inside, at least until the socks begin their usual mysterious migration. The phrase inside carries a comfortable picture with it. It assumes a boundary and a space enclosed by that boundary. It assumes that smaller things sit within larger things the way peas sit in a tin or books sit on a shelf. But quarks do not obviously belong to that kind of picture. If a quark is truly elementary, then it may not have an inside in the spatial sense at all. It may not be a tiny bead filled with even tinier machinery. It may be more like a Pointlike ingredient in our best theories, not because it has literally zero size in some naive cartoon way, but because every experiment we have so far performed has failed to reveal internal structure. That is a subtle but important distinction. Physics is often careful in ways everyday language is not. It does not always say this thing has no inside, full stop. More often, it says we have found no sign of internal structure down to the scales we have probed, which is less dramatic, perhaps, but also more honest. This is one of the quiet tensions at the heart of science. We want final answers. Science usually offers the best answer available under current evidence, with a polite note attached saying subject to revision if the universe gets any ideas. And the universe very often does get ideas. So as we settle into this question, we need to hold two possibilities at once. The first is that quarks really are elementary, and asking what happens inside one is a bit like asking what happens inside the concept of left. The second is that quarks only appear elementary because our current tools and theories have not yet reached beyond them. In that case, the question is not foolish at all. It is simply early. There is a long tradition in physics of mistaking the current floor for the bottom of the building. People have done it with atoms, with nuclei, with protons and neutrons, and perhaps one day people will chuckle gently at our confidence regarding quarks too. Or perhaps not. Perhaps quarks are genuinely among the final cast of characters we do not yet know. And this not knowing is not a flaw in the story, it is the story. Now, when people first hear the word quark, there is often temptation to imagine something like a tiny hard pellet. That is understandable. The mind likes objects with edges. It likes things that can be visualized as miniature versions of familiar stuff. Even atoms are often drawn like little solar systems, despite that picture being only partly useful and often misleading. But the subatomic world resists that kind of common sense. A quark is not a crumb of matter in the way a grain of sand is a crumb of rock. It does not sit there with a neat little surface waiting to be sliced open. It is described by quantum fields, by probabilities, by properties such as flavour and colour charge that sound almost playful until one realises they are part of a serious mathematical framework. That phrasing alone can make the whole subject sound remote and forbidding, but it need not be. The strangeness of quarks is not a sign that the world has stopped making sense. It is a sign that our everyday intuitions were built for chairs and apples and hot tea, not for the contents of atomic nuclei. We evolved to judge distances we can walk, speeds we can run, objects we can throw, and perhaps, on a very good day, whether a loaf in the oven has another few minutes left. We did not evolve to picture entities that cannot exist alone, carry a kind of charge unrelated to literal colour, and spend their lives bound up by gluons inside particles that themselves are not nearly as simple as school diagrams suggest. And yet we can learn to think about them, just as people learn to think about the Earth moving around the Sun, or time behaving differently near great speed and gravity, or empty space seething with activity instead of sitting quietly as a vacuum in the common sense picture. The history of physics is, among other things, the history of ordinary intuition being politely escorted off the premises. There is also something very human about wanting to know what is inside a quark, even if the answer may be nothing in the usual sense. The question comes from more than technical curiosity. It comes from a suspicion that reality may still be holding something back. It comes from the same place that asks what lies beyond the visible universe, whether black holes destroy information, or why the constants of nature take the values they do. We are not merely interested in facts. We are interested in whether there is another layer behind the layer we currently understand. That desire can be noble, and it can also be a bit comical. One imagines the universe as a patient host, and human beings as guests who keep peering into cupboards and saying, "Sorry, just one more question. Only one more," and then, naturally, another. The universe has so far been accommodating, though not always in the tone we might prefer. If we're going to ask what happens inside a quark, then the first thing we must do is step back from the word inside and examine our habits of thought. We tend to assume that smaller always means more detailed, that every object is made of smaller objects and those of smaller ones still. It is a nesting instinct of the mind. But physics does not guarantee an endless ladder downward. It allows the possibility, certainly. Yet it also allows that some descriptions may bottom out, not because imagination has failed, but because nature itself is built from entities that are not composed in the way larger things are. That possibility can feel unsatisfying at first. We are used to explanation by decomposition. What is a table made of? Wood. What is wood made of? Fibers and molecules. What are molecules made of? Atoms. What are atoms made of? Nuclei and electrons. What are nuclei made of? Protons and neutrons. What are they made of? Quarks. And then we ask, and what are quarks made of? We want the next rung. We almost resent the universe if it answers with silence or says, perhaps there is no next rung, at least not of that kind. Still, silence in physics is rarely total. Even when we cannot say what something is made of, we can ask how it behaves, how it interacts, what patterns it obeys, how it reveals itself indirectly. A quark may resist being opened like a box, but it does not resist being studied. Not easily, certainly, not politely, but not completely. We know quarks come in different types. We know they help build the particles around us. We know they are held together by the strong interaction, carried by gluons. We know the inside of a proton is far busier than a simple picture of 3 static quarks would suggest. Already that gives us an interesting twist on tonight's title. Perhaps the better question is not what happens inside a quark, but what happens where quarks live, how they behave, and whether the idea of an inside survives contact with the smallest scales. That is where things begin to get really interesting. Because even if a quark itself has no internal machinery that we can presently detect, the world around quarks is anything but simple. The proton, for example, is not a neat bag containing 3 marble-like components sitting still and minding their own business. It is a restless, dynamic system full of exchange, motion, and fleeting activity. Quarks inside it are not just occupants. They are participants in something more like a continual quantum negotiation, with gluons passing influence between them, and short-lived quark pairs appearing and disappearing in the background. In other words, even before we ask whether a quark has an inside, we have to understand that the matter around it is already much stranger than the old textbook cartoons let on. And perhaps that is a good place to settle for now, because the path toward the inside of a quark, or the realization that there may be no such inside to inspect, begins with a more practical question. How did physicists come to believe quarks were there in the first place, hidden within protons and neutrons, if no one ever found one sitting alone and waiting to be introduced? It helps, before we go any deeper, to remind ourselves what sort of world quarks belong to in the first place. We throw around words like matter, particles, atoms, and quarks as if they sit in a neat little row, each one patiently waiting for its turn. But most of us do not actually walk through life thinking about the structure of things in that order. We think in chairs and clouds, kettles and trees, sleeves and spoons. We think in surfaces, weight, texture, warmth, and inconvenience. We notice when bread goes stale, when socks go missing, when the tea is too hot to drink and then somehow, 3 minutes later, slightly disappointing. The world arrives at human scale, and human scale is not especially honest about what things are made of. A table feels solid, a mug feels simple, a stone feels like the very definition of a single thing, and yet each of those ordinary objects is less like a uniform block and more like a crowded arrangement of smaller pieces held together in a way that only looks calm from a distance. This is one of the nicest tricks nature plays on us. It lets large things seem straightforward, while their smaller ingredients behave in ways that are anything but. So when we say that quarks are among the tiny things that make almost everything, we are really saying something both grand and oddly domestic. Your hands, your lungs, the paper of an old book, the metal springs in a mattress, the dust on a windowsill, the crust of the earth, the moon hanging above it, and the stars that lit the heavier elements long before your breakfast plate ever had a chance to exist, all of these belong to the story of ordinary matter. Not all of reality, certainly. The universe is under no obligation to consist only of the kinds of things we're used to bumping into. There is light, which is not made of quarks. There are neutrinos, which are shy in a way that almost seems personal. There is dark matter, which may be rolling its eyes at us from behind the scenes, while we continue to guess badly about what it is. But nearly everything you can touch in the everyday sense, nearly everything that builds the visible world of bodies, objects, mountains, crumbs, and rather ambitious furniture, comes down eventually to a very small cast of characters. At first glance, that sounds comforting. We like the idea that complexity can be reduced to a manageable few ingredients. It suggests a recipe. It suggests that once we know the components, the whole universe will become neat and cooperative. Physics has had to disappoint that hope many times, but it does at least preserve the wonder of it. The ingredients may be few, yet the ways they combine are staggeringly rich. The old philosophical dream was that beneath all the clutter of experience there must be some basic stuff from which the rest is made. Different civilizations imagined different answers. Some favoured earth and air and fire and water. Others proposed indivisible units, tiny seeds of matter too small to see. For a long while these were clever guesses rather than experimentally grounded conclusions. Human beings suspected a hidden architecture to the world long before they had the tools to test it properly. That is one of our better habits. We often begin by being wrong in the right direction. Eventually the atom became the serious answer, not at once, and not without resistance, but gradually the evidence stacked up. Matter behaved as though it were made of discrete units. Chemical reactions made more sense that way. The regularities of the periodic table made more sense that way. Gases, heat, and motion began to make more sense that way. It turned out that matter was not continuous after all, but grainy. The world, when looked at carefully enough, came in packets. That alone is already strange if you stop and sit with it for a moment. A piece of iron feels smooth and uninterrupted. Water looks like a continuous liquid. The air in a room seems like nothing more than a gentle presence, if that. Yet all of them are collections of atoms, moving, colliding, binding, vibrating, never perfectly still. The calmness of everyday life is often just the average appearance of immense microscopic activity, a bit like looking at a city skyline from far away and assuming everyone inside the buildings is behaving sensibly, which, as we know, is a dangerous assumption. Atoms, though, were not the final flaw. Once people learned more about them, the atom itself turned out to be mostly space, with a compact nucleus at the centre and electrons arranged in a cloud around it. That revelation changed our picture of matter in a very fundamental way. Solid objects are not solid because they are densely packed lumps all the way through. They are solid because of the interactions among their parts, especially the quantum rules that prevent atoms from simply collapsing into one another. What feels like firmness in a table is not little billiard balls stacked with no gaps. It is structure, force, and exclusion, producing the sensation of solidity on the scale, where you and your knees make contact with furniture. Inside the nucleus, things become denser and stranger. The nucleus contains protons and neutrons, and for a while those seemed like the obvious endpoint. It would have been a tidy place to stop. One can imagine a certain scientific exhaustion setting in. Very good, atoms are not indivisible, but surely the nucleus gives us the truly fundamental chunks. Let us all go home, make a sandwich, and stop opening containers. Sadly, for anyone hoping for a quick finish, the universe had not yet exhausted its supply of hidden compartments. Protons and neutrons are made of quarks. More specifically, the ordinary matter around us is built mostly from just two kinds of quarks, known as up quarks and down quarks. Those names are a reminder that physicists are capable of revolutionary insight and underwhelming naming in the same lifetime. A proton contains two up quarks and one down quark. A neutron contains two down quarks and one up quark. Rearranging just those ingredients produces the two particles that sit in atomic nuclei and account for the bulk of the mass of ordinary matter around us. Now that can sound almost disappointingly simple when said quickly. Two kinds of quarks, mixed in small combinations, building the protons and neutrons that build the nuclei of atoms that build the material world. Rather elegant, almost suspiciously elegant. But the elegance hides a great deal of complication, because quarks are not sitting quietly inside protons and neutrons like peas in a pod. They are bound together by gluons, and the entire interior of a proton is a very lively place. Even so, if we're only drawing the broad map at first, then yes, most of the visible matter you know comes down to up quarks, down quarks, and electrons, along with the forces that allow them to organize themselves into atoms and molecules and eventually into things as varied as coral reefs, violin strings, rain puddles, and disappointing office biscuits. It is worth pausing over the phrase almost everything, because it does some careful work. You're not made only of quarks. Electrons matter enormously. Without them there are no atoms in the familiar sense, no chemistry, no molecules, no bonds, no tissues, no pages to turn, no tea to spill. Yet electrons are not made of quarks. They belong to a different family. So even in ordinary matter, the world is not built from one universal brick, but from a small set of ingredients with different roles. Quarks give us the heavy central cores of atoms, while electrons shape the chemistry that makes those atoms interesting. That distinction matters because people sometimes imagine matter as though it were a single substance chopped into smaller and smaller cubes. It is more like a cast of players, each with particular properties, interactions, and limits. Quarks do not simply behave like miniature versions of apples or stones. Electrons do not orbit in the tidy planetary way older diagrams suggest. Forces are not little ropes or pushes in the everyday sense. The deeper physics goes, the more careful language has to become, because every familiar picture helps for a while and then starts quietly lying to you. Still, some pictures remain useful if handled gently. Think of the visible world as a colossal arrangement of patterns built from a modest alphabet. The alphabet is small, but the words it can form are astonishing. With just a few letters, one can write shopping lists, love letters, detective novels, bad poetry, government forms, and stern notes about whose turn it is to do the washing up. Matter is rather like that. A relatively small set of fundamental ingredients can generate a bewildering variety of structures, from bacteria to blue whales, from candle soot to cathedral stone, from fingernails to meteorites. Chemistry enters here as the art of combination. Once nuclei and electrons are in place, atoms acquire different personalities depending on how many protons are in the nucleus and how the electrons arrange themselves. Hydrogen behaves one way, carbon another, oxygen another still. With those differences comes the possibility of bonding, and with bonding comes the extraordinary library of molecules. Water, sugars, proteins, minerals, plastics, perfumes, paper and skin all emerge from different combinations of atoms, which themselves emerge from arrangements involving nuclei, which themselves depend on quarks. The scale difference is enormous, but the continuity is real. The bread on your kitchen counter and the star that forged many of its atoms are connected by a chain of physical history that runs all the way down. And yet quarks are not the whole story even of the mass of matter. This surprises many people the first time they hear it. One might assume that if a proton is made of 3 quarks, then the proton mass is mostly just the sum of the masses of those quarks. But that is not really how it works. A significant portion of the mass of ordinary matter arises from the energy of the strong interaction inside protons and neutrons. The gluons and the motion and binding dynamics inside these particles contribute heavily to what we ultimately experience as mass. So even the familiar statement that things are made of quarks needs refinement. Matter is not only assembled from ingredients, it is also shaped by interactions, by restless internal activity, by the energy tied up in confinement. This is one of the reasons particle physics can feel so slippery. The deeper we go, the less satisfying it is to picture things as mere tiny objects. Relations matter, fields matter, interactions matter. A proton is not simply a container holding 3 permanent hard beads. It is a quantum system. Stable enough to help build atoms, yes, but internally dynamic. The visible world rests on structure that is more active and less static than the old mechanical imagination would prefer. Perhaps that is why the topic is so captivating in a sleepy sort of way. The ordinary world keeps turning out to be built on hidden commotion. The spoon appears still, yet its atoms are jiggling. The atom appears compact, yet it is mostly structured emptiness. The proton appears simple, yet it is busy inside. And the quark, which sounds like it ought to be one of the final calm points in the story, arrives with its own bundle of strange rules and unanswered questions. Nature has a consistent habit of putting complexity where simplicity first seemed likely. There's also an emotional oddity to this kind of knowledge. Learning that we're made from tiny ingredients can make a person feel either reduced or enlarged depending on the mood of the evening. On the one hand, it can sound flattening. You are atoms, quarks, electrons, chemical reactions, and the usual biological fuss. On the other hand, it can feel astonishingly expansive. The same basic ingredients appear in stars and seas and skin and stone. The matter in your body is not separate in kind from the matter in the wider cosmos. It has been borrowed, rearranged, and animated for a while. There is something oddly calming in that, provided one does not think about tax forms at the same time. Yet for all the beauty of that connection, physics remains properly cautious. When it says that tiny things make almost everything, it does not mean that knowing the tiny things automatically explains the whole richness of lived reality. It explains the material basis. that is not the same as explaining every pattern that can arise from that basis. A sonnet is made of letters, but letters do not by themselves account for why one line lingers in the mind while another falls flat. A body is made of particles, but particles do not save you the work of biology, chemistry, physiology, or experience. Layers of explanation do not cancel one another, they stack. This is worth keeping in mind because reduction can be a little overconfident if left unattended. It is true that your bones, your breath, and the wall behind you depend on tiny constituents. It is also true that one does not understand a cathedral by grinding it into powder and describing the mineral content. The lower levels matter deeply, but so do the structures built from them. Physics gives us the ingredients and the rules. Higher levels of science tell us what those ingredients manage to become when the combinations get elaborate enough. Still, there is a special thrill in tracing the line downward. The mug on the bedside table is ceramic. Ceramic is built from compounds. The compounds are made of atoms. The atoms have nuclei and electrons. The nuclei contain protons and neutrons. The protons and neutrons contain quarks. By the time one reaches that scale, the path from tea mug to quark feels almost absurd, yet it is real. The ordinary object and the fundamental constituent belong to one continuous world. The distance between them is a matter of scale and description, not of separate realities. That connection also changes how we think about emptiness. Most of what we call matter is not packed full in the common sense way. Atoms are spacious in relative terms. Their nuclei are tiny compared with the regions occupied by electron clouds. The nucleus itself is small compared with the atom, yet densely concentrated. Protons and neutrons are smaller still, and within them quarks abound in ways that resist simple visualization. So the solid world is not a stack of little hard marbles all the way down. It is a hierarchy of organization, with different rules becoming important at different scales. And once you accept that, the question of a quark becomes more interesting, not less. We're no longer merely asking for the next smaller thing. We're asking what sort of entity a quark is at all. Is it best understood as a point-like excitation of a field? Is it a permanent constituent? Is it perhaps emergent from something deeper? Does asking what it is made of even make sense within our current framework? Those questions only become visible after you first appreciate the layered structure of ordinary matter and the peculiar route by which almost everything familiar depends on a small and rather unruly collection of microscopic ingredients. There is another gentle surprise hidden in this story. The world is not made of the most exotic particles in the physics catalogue. There are heavier quarks, stranger particles, and short-lived creatures produced in energetic environments. But the everyday universe near us is remarkably conservative. It relies mostly on the simplest durable combinations. This has a certain domestic logic to it. The universe, for all its flamboyant possibilities, does most of its housework with a fairly modest toolkit. The rare and glamorous particles come and go in high-energy events, while ordinary matter gets on with the business of being rock, rain, skin, salt, and bread. That simplicity at the everyday level is part of what makes the deeper questions possible. Because matter is built from repeating patterns, physicists can study those patterns, collide particles, examine scattering results, and infer structure. If every stone and every lung and every apple were built from completely different kinds of stuff, the project would be far messier than it already is, which is saying something. Instead, the same few ingredients keep returning in different arrangements, and that repeatability gives science its foothold. So by the time we arrive back at quarks, we have already learned something important. They are not merely tiny because tiny things are fashionable in physics. They matter because they sit in a structural chain linking the deep subatomic world to nearly everything we can see and touch. They help make protons and neutrons, which help make nuclei, which along with electrons make atoms, which build molecules, which compose materials, bodies, landscapes, instruments, and all the countless objects that furnish human life. It is an extraordinary reach for something so elusive. And of course, once you realise that, another question begins to stir quite naturally. If quarks are so central, if they help build the protons and neutrons inside every atom of ordinary matter, then how on earth did physicists figure out that they were there at all? Especially given that quarks do not wander about alone where anyone can simply spot them and say, "Ah yes, there you are, just as suspected." When most people first hear that a proton contains quarks, the picture that springs to mind is tidy enough to fit on a school poster. One imagines 3 tiny particles tucked neatly inside, perhaps a bit like peas in a pod, or 3 marbles rattling around in a very small box. It is a useful first image, and like many useful first images in physics, it becomes less accurate the longer you stare at it. The proton is not a miniature container with 3 hard little items sitting quietly at fixed positions, patiently waiting to be counted. It is not calm, and it is not simple, and it is certainly not empty except for a few permanent residents. The deeper physicists looked, the more the proton began to resemble a crowded and restless interior rather than a tidy arrangement. Yes, the old picture captures something important. There are 3 quarks that give the proton its essential identity, 2 up quarks and 1 down quark. Those are often called the valence quarks, which is a slightly formal way of saying the quarks that carry the basic defining content of the particle. If you want to know why the proton is a proton and not a neutron or something stranger, those 3 quarks are part of the answer. But they are not the whole answer, and they are not the whole story of what is inside. To understand why, it helps to let go of the idea that the proton is built like a tiny machine with fixed parts. It is better to think of it as a quantum system held together by the strong interaction, with motion, exchange, and constant internal activity. The quarks are bound together by gluons, and those gluons are not merely little bits of glue in the everyday sense, sitting quietly between quarks and minding their own business. They are the carriers of the strong interaction, and unlike some of the other force carriers in physics, they can interact with each other as well. That one detail makes the proton far busier than a common sense picture would suggest. So if you could somehow peer into a proton, not with a microscope in the ordinary sense, because nothing about this scale behaves politely enough for such methods, but with the insight built from scattering experiments and quantum theory, you would not find 3 quarks parked in place like furniture in a tiny room. You would find a dynamic interior. You would find quarks moving in a way that is not classical motion exactly, because the word moving starts to mislead at these scales if taken too literally, but still something active, distributed, and energetic. You would find gluons being exchanged continually. And you would also find fleeting quark and antiquark pairs appearing and disappearing as part of the proton's ongoing inner life. That last part tends to surprise people. If the proton is supposed to be made of 3 quarks, what are all these extra quarks doing there? The answer is that in the quantum world, a particle is not merely its permanent roster. The strong interaction is energetic enough, and quantum fields are lively enough, that the interior of the proton includes temporary contributions from what are sometimes called C-quarks. These are not part of the basic valence structure that defines the proton, but they are very much part of its physical reality. For brief moments, quark and antiquark pairs can emerge from the energy and then vanish again. The proton is not breaking apart when this happens. It is simply being itself, which turns out to be a more crowded and fluctuating business than early diagrams ever suggested. This is where the word heart becomes oddly appropriate, not in a sentimental sense, but in the sense of a centre that is active rather than inert. The inside of a proton is not a dead core. It is a place of structured unrest, and that unrest matters because the proton's measurable properties do not come only from the 3 valence quarks standing quietly in the spotlight. They arise from the total system, including the gluons, the C-quarks, and the ceaseless interplay among them. Even the proton's mass is a good example of this. It is tempting to imagine that the proton simply weighs what its 3 quarks weigh when you add them together. That would be a very ordinary sort of bookkeeping, and the universe on small scales has limited patience for ordinary bookkeeping. The proton's mass comes largely from the energy of the strong interaction within it. The quarks inside are light compared with the final mass of the proton. Much of what we experience as the proton's mass is bound up in the motion and interaction energy inside this confined system. In other words, the proton is heavy not merely because of what it contains in the simplest ingredient list, but because of how furiously and tightly those contents behave. There is something almost philosophical about that. A proton is not just a set of things, it is a pattern of activity. That pattern is stable enough to persist, to sit in nuclei, to help build atoms, rocks, oceans, lungs, and library shelves, yet inside it there is no stillness in the ordinary sense. Stability at this level does not mean inactivity. It means a reliable overall identity emerging from constant internal motion. Now, when physicists tried to learn what was going on inside protons, they could not simply open one up and have a look. Instead, they used collisions. They fired high-energy particles at protons and studied how those projectiles scattered. This was rather like learning the layout of a dark room by throwing small objects into it and listening carefully to the pattern of impacts. Except, of course, the room was unimaginably tiny. The objects were elementary particles, and the listening was done with vast detectors and formidable mathematics. One should never let anyone tell you science has no dramatic flair. It simply expresses it in a slightly bureaucratic way. These experiments revealed that the proton's interior does not behave as though it were smooth. It behaves as though the incoming particles are striking smaller constituents inside. That was one of the major clues that quarks were real physical ingredients rather than just mathematical conveniences. But the results also showed that the distribution of momentum inside the proton was more complicated than a simple three-part division. The valence quarks do carry some of the proton's momentum, certainly, but a large share is carried by gluons. This is one of the great quiet surprises of proton structure. The particle most people think of as being made of three quarks turns out to depend enormously on gluons for its inner economy. So the proton's crowded heart is not only crowded in the sense of containing brief extra quark activity, it is crowded with responsibility. The quarks define the identity, the gluons provide much of the internal binding and momentum carrying, and the C contributes to the full quantum picture. Nothing sits entirely apart from the rest. The proton is a community, if a highly argumentative one, held together under rules that would make ordinary social life seem blissfully simple. There is also the question of size, which sounds straightforward until it becomes slippery. We can speak of a proton having a certain scale, and experiments can probe its effective size, but the interior is not organised with crisp boundaries the way a toy ball is. The quarks are not tiny peas sitting at known distances from a central point. Quantum entities are described through probabilities and interactions, not through miniature classical orbits. If you try too hard to picture the proton as a little solar system, the picture will betray you almost at once. The proton has structure, yes, but it is quantum structure, and that means it is spread out, relational, and governed by rules that do not resemble the mechanics of household objects. One of the reasons this is difficult to picture is that our brains are tuned to the middle world. We are very good at imagining apples in bowls and shoes under beds. We are less good at imagining confined quarks whose positions and momenta are not sharp in the classical sense, all embedded in a sea of gluonic activity. Evolution, for all its virtues, did not prepare us for the proton. It prepared us for avoiding cliffs and locating soup. The fact that we can think about proton structure at all is already rather impressive. And still, the temptation to oversimplify remains strong. It is understandable. Teachers need first steps. Textbooks need diagrams. Videos need illustrations that do not immediately send viewers off to lie down in a dark room. So the three-quark picture survives because it is not false so much as incomplete. It tells you what kind of particle the proton is. It does not tell you what life is like inside. And life inside, if one may borrow the phrase, is much more animated. Imagine a city seen from very far above at night. From a distance it might look like a stable shape, a tidy cluster of lights, a fixed thing on the landscape. But as you move closer, the calm outline dissolves into traffic, signals, deliveries, arguments, heating systems, restless pets, forgotten keys, and people trying to remember why they walked into the kitchen. The proton is a little like that. From far away, it behaves as a stable particle with definite charge and mass. From closer inspection, it becomes a place of circulation and exchange. The strong interaction is responsible for this rich interior life. It is enormously powerful at short distances, and it binds quarks in a way that does not fade into simple detachment. This is important because it means the proton is not just crowded by accident. Its crowding is built into the nature of the force that governs it. The gluons that mediate the strong interaction are themselves able to carry the very property they act upon, which makes the whole system self-involved in a way that electromagnetism, for example, is not. Light can pass through light without much fuss under ordinary conditions. Gluons are not so aloof. They participate in the drama directly. Because of this, the proton's interior can be thought of less as a box of components and more as a knot of field activity. That phrase may sound abstract, but it captures something important. The real substance of the proton lies not in a handful of little hard chunks sitting still, but in an organized excitation of underlying fields. The quarks matter, the gluons matter, their interactions matter at least as much as the itemized list of constituents. At small scales, being is inseparable from doing. There is another quietly fascinating issue here, which is spin. The proton has an intrinsic angular momentum, a quantum property known as spin, and for a long time physicists assumed they could account for it mainly from the spins of the three valence quarks. That turned out not to be sufficient. The proton's spin, like so much else about it, emerges from a more complicated combination of contributions. The spins of quarks matter, yes, but so do the gluons and the orbital motion within the system. Once again, the proton refuses to be reduced to a simple sum of three permanent pieces. Even one of its most basic properties comes from the crowded totality. This has given rise to decades of careful investigation, and it is one of those lovely cases where science becomes more interesting by becoming less tidy. A simple answer would have been easy to print and easy to memorize. Instead, physicists found themselves confronting a system that insists on depth. The proton does not surrender its secrets all at once. It yields them piece by piece through experiments, models, revisions, and the occasional humbling reminder that nature is under no obligation to resemble the first diagram in a textbook. Of course, one might reasonably ask how something so busy can remain stable. If the interior is full of exchange, fluctuations, and temporary pairs, why does the proton not simply unravel? The answer lies in the very same strong interaction that makes the interior lively. The forces and rules at work do not produce disorder in the everyday sense. They produce a stable bound state, one whose internal dynamics are part of what keeps it together. The proton is not stable despite its activity. It is stable through it. That kind of stability can be hard to appreciate because our common sense often associates permanence with stillness. A building seems stable because it does not move. A sleeping cat seems stable because it has decided for the moment not to knock anything off the shelf. But at deeper levels of nature, stability can emerge from ongoing motion and interaction. A whirlpool keeps its form through flow. A living body remains itself through metabolism. A proton remains a proton through the confined dance of quarks and gluons. The appearance of calm at larger scales is sometimes the outward face of continuous inner work. And that brings us back to the central idea of this part of the journey. The proton's heart is crowded not because physics enjoys being difficult, though it certainly has its moments, but because the true structure of ordinary matter is richer than the old solid lump picture ever allowed. The proton is one of the core building blocks of the visible world, yet inside it there is no neat silence. There are valence quarks, yes, but also gluons carrying force and momentum, and C quarks flickering into brief existence, and contributions to mass and spin that come from the total arrangement rather than from a simple head count. Once you start to see the proton this way, a change comes over the whole subject. Matter stops looking like stacked little stones and begins to look like organised activity at every scale. The stable world is built from unrest that holds together. The smallest ingredients are not merely tiny objects, but participants in systems of exchange, confinement, and field behaviour. Even the humble proton, tucked quietly into every atomic nucleus, turns out to contain a more crowded interior than anyone first imagined, and the more crowded that interior appears, the more pressing another question becomes. If quarks are bound so deeply into this restless heart, if the proton depends on their confinement rather than their freedom, then why is it that no one ever finds a single quark wandering loose on its own, as though it had simply stepped out for air? That question takes us directly to one of the strangest rules in the subatomic world, because if quarks are so central to matter, and if protons and neutrons are full of them, why can we not simply pry one loose and examine it on its own? The short answer is that quarks are held by the strong interaction, and the strong interaction is not built with the sort of manners we are used to from ordinary forces. It does not behave like a polite spring that weakens the farther you pull. It does not fade away in the simple way common sense would hope. In fact, one of its most famous habits is that it refuses to let go. Now that phrase can sound melodramatic if you're not used to particle physics. A force that refuses to let go sounds less like science, and more like the plot of an overcommitted detective novel. But it is a fair description of what happens. The strong interaction binds quarks together inside protons and neutrons, and it does so with such determination that isolated quarks are not observed in the world around us. We do not find them drifting through space like tiny grains. We do not trap one in a bottle. We do not place one on a table beside an electron and compare notes. Quarks remain confined inside larger particles, and when we try to separate them by pouring in enough energy, the result is not a lone liberated quark. The result is usually the creation of new particles. Nature responds to our tugging by rewriting the company arrangement rather than allowing a clean resignation. To appreciate why this is so unusual, it helps to compare the strong interaction with something more familiar. Take gravity. Gravity pulls two objects together, but if you move them far enough apart, the pull weakens. The same is true for electricity and magnetism in the broad everyday sense. The farther apart charges or magnets get, the less strongly they influence one another. We are used to forces that thin out with distance, like gossip losing detail as it travels down the street. The strong interaction is different. Between quarks, the binding does not simply dwindle away as separation increases. Instead, the energy stored in the connection grows. It is often compared, cautiously, to stretching a band that becomes more demanding the farther you pull. That comparison is useful up to a point, though like all comparisons in physics, it eventually begins to groan under the strain. Still, it gets one vital idea across. Pull two quarks apart, and you do not easily weaken their bond into irrelevance. You pump more and more energy into the system, and because energy can turn into mass in particle physics, at a certain point it becomes energetically favourable for the system to create a new quark and antiquark pair. So rather than producing one lonely free quark, you end up with new bound particles. The attempt to isolate a quark simply gives you more hadrons, which is the family name for particles built from quarks, including protons, neutrons, and mesons. It is a bit like trying to separate a stubborn pair of dancers, only to discover that the ballroom has spontaneously produced more couples. This property is known as confinement, and it is one of the defining features of quarks. Confinement means that quarks are never found alone under ordinary conditions. They come packaged in combinations that are allowed by the rules of the strong interaction. Protons and neutrons are built from three quarks. Mesons are built from a quark and an antiquark. There are also more exotic combinations that physicists have uncovered, but the essential point remains. Quarks live in groups. The strong interaction is not a casual arrangement. It is a binding law of remarkable insistence. The carriers of this interaction are gluons. and their name, charmingly enough, gives a decent first impression. Gluons do help hold quarks together. But if the word glue makes you imagine something passive and sticky, sitting quietly between pieces of a broken vase, that picture will not survive long. Gluons are active participants in the proton and neutron interior. They are not merely a filler between quarks. They carry the strong interaction. They transfer a special property called color charge, and crucially, they can interact with each other. That last feature is one of the great reasons the strong interaction is so unlike the electromagnetic one. Photons, the carriers of light and electromagnetism, do not carry electric charge in the way electrons do, so they do not generally cling to one another in ordinary circumstances. Gluons are different. They carry the charge relevant to the strong interaction, which means the force carriers themselves participate in the force network. This makes the whole business more self-involved, more tangled, and much harder to picture in everyday terms. The strong interaction is not just quarks passing messages through neutral couriers. The couriers are part of the argument. Now the term color charge deserves a careful introduction, because it is one of those phrases that sounds almost unserious until you realize it is a standard part of the theory. Quarks come in 3 types of color charge, conventionally called red, green, and blue. These are not literal colors. Nobody has discovered a tiny crimson quark glowing politely in the dark. The names are simply labels for a mathematical property that governs how quarks interact through the strong force. Gluons carry combinations of these color charges and mediate changes among quarks in a way that keeps the whole bound state color neutral overall. This can seem needlessly whimsical at first, but the naming has a certain convenience. It helps remind us that the strong interaction needs more than the simple, positive and negative distinction of electricity. Quarks combine in such a way that the final particles, like protons and neutrons, are color neutral. In a rough analogy, 3 different color charges can combine to form a balanced state, just as a quark and an antiquark can pair in a way that cancels the relevant charge. Again, it is not a statement about literal color. It is a bookkeeping language for the theory. Particle physics sometimes sounds like it was developed by a committee containing both stern mathematicians and at least one person who had not entirely lost their sense of mischief. The full theory describing quarks and gluons is called quantum chromodynamics, which is a grand name for an arrangement that is both elegant and uncooperative. It is elegant because it accounts with impressive success for the behaviour of the strong interaction. It is uncooperative because the equations become extremely difficult to solve in the regime where quarks are tightly bound inside hadrons. In simpler terms, we understand the rules well, but the consequences of those rules in the messy interior of a proton are not the sort of thing one jots down on a napkin while waiting for soup. Yet even without diving into the harder mathematics, we can grasp the central features. At very short distances, quarks behave in a surprising way. They interact more weakly. This property is called asymptotic freedom, and it means that when quarks are extremely close together, the strong interaction loosens its grip somewhat. Not entirely, but enough that quarks inside a proton at high energy can behave as though they are less tightly bound during brief violent encounters. This was one of the key theoretical and experimental insights that helped explain results from high-energy scattering experiments. So the strong interaction has a dual personality that is almost rude in its cleverness. At very short distances it becomes weaker. At larger separations it becomes stronger. That is the opposite of what ordinary intuition expects. One might almost admire the perversity of it if it were not so inconvenient for anyone trying to form a simple mental picture. But this behaviour explains 2 of the defining facts about quarks. First, why high-energy experiments can probe them as though they are more nearly independent inside hadrons. Second, why we do not observe them freely wandering about afterward. Close up, they are relatively freer. Try to pull them apart and the force tightens again. That pattern makes the inside of a proton very different from a little box of marbles. The quarks are confined, yes, but not by rigid walls. They are confined by the very structure of the field interactions among them. The gluon field between quarks stores energy. Stretch that field and you do not get a gentle loss of connection. You get more tension, more stored energy, and eventually new particle production. The strong interaction is less like a thread that snaps and more like a situation that escalates. There is something deeply important here for the story of matter. Confinement is not a technical footnote. It is the reason quarks contribute to the world in the way they do. If quarks could roam freely, the structure of matter would be utterly different if stable familiar matter existed at all. Protons and neutrons depend on this binding. Atomic nuclei depend on protons and neutrons. Atoms depend on nuclei. Chemistry depends on atoms. So the firmness of the visible world, the durability of everyday matter, traces part of its lineage to a force that refuses to release the constituents at the heart of the nucleus. It is also worth noticing that the strong interaction works on two related levels, and the distinction can be slippery if one is not careful. There is the fundamental strong interaction between quarks, mediated by gluons. Then there is the residual strong force that acts between protons and neutrons in the nucleus. That residual force is what binds nuclei together. It is a leftover effect, rather like the way neutral molecules can still attract each other through residual electrical influences. The force inside the proton and the force between protons and neutrons are related, but they are not identical in their immediate description. Without that residual binding, nuclei would not hold together properly. Without the deeper quark-level binding, protons and neutrons would not exist in the first place. All of this begins to explain why the proton is not just crowded, but inseparable from the force that fills it. The valence quarks are there, certainly, but the gluons are not simply the background staff. They are central to the whole enterprise. In fact, gluons carry a significant fraction of the proton momentum, and their interactions help generate much of the proton mass through energy. This is a remarkably modern kind of statement. It tells us that what a thing is cannot be separated neatly from what its forces are doing. In the small-scale world, the old distinction between object and interaction becomes less tidy. A proton is what its quarks are, yes, but also what its gluons are doing. Now, if one is in a patient mood, and I hope tonight we are, it is helpful to ask why the strong interaction was not obvious long before modern physics. The answer is scale. Its effects dominate at tiny distances, within atomic nuclei and within hadrons, but on human scales they do not announce themselves directly. Chairs do not cling to walls because of the strong interaction. Biscuits do not remain attached to saucers through gluon exchange. The force is intense, but its range in the residual nuclear form is short, and the deeper confinement form is hidden inside hadrons themselves. It takes specialized experiments and theory to uncover it. Nature has tucked one of its strongest forces into one of its smallest domains, and because it is hidden there, it can seem almost unbelievable the first time one meets it. A force stronger than electromagnetism, stronger than gravity by an absurd margin at the scales where it matters, and yet absent from ordinary awareness. It is like learning that inside every quiet village there is a steelworks running around the clock, but only at a scale too small for any passerby to notice. Once you know it, the world feels the same and not the same. There have even been moments in physics where researchers try to recreate conditions under which quarks are not confined in ordinary hadrons. In extremely hot and dense environments, such as those believed to have existed shortly after the Big Bang, quarks and gluons can form a state called quark-gluon plasma. In this state, the usual hadronic boundaries loosen, and quarks and gluons move in a more collective medium, rather than being locked into individual protons and neutrons. This is not the same as keeping isolated quarks around like pets in a laboratory. It is more like melting the usual particle structure into a very hot, dense soup. The fact that such a state can exist tells us confinement is powerful, but also dependent on conditions. Under ordinary present-day conditions, confinement rules. Under extreme early universe conditions, matter behaved differently. That is an extraordinary thing to consider while sitting quietly in bed or on a sofa. The visible world around you is built from particles whose constituents are trapped by a force so stubborn that only the most extreme temperatures and densities can loosen the arrangement into something more fluid. The calm mug on the nightstand, the frame of the window, the bones in your hand, all of them are descendants of a universe that once ran hot enough to scramble the very bound states that now make ordinary matter possible. We tend to think of stability as the default state of existence, but often it is the cooled outcome of earlier chaos. Still, even in calmer conditions, the proton never becomes dull. The gluons continue their exchanges. C-quarks continue to flicker in and out. The valence quarks remain confined, and the whole internal system continues its restless life. The force that refuses to let go is not only a jailer, it is also the architect of structure. It creates the conditions under which quarks can form durable particles, and those particles can then build nuclei, atoms, and the rest of the visible world. Refusal, in this case, is creative. That may sound like an overgenerous thing to say about a force, but the more one studies physics, the more clear it becomes that constraints are often what make complexity possible. Without the rules that bind, matter would not assemble. Without confinement, quarks would not produce the particles that give atoms their centers. Freedom is not always the recipe for structure. Sometimes what allows the world to exist in a stable, inhabitable way is precisely the fact that some of its deepest constituents cannot simply wander off. So when we imagine quarks and gluons together, we should not picture a static prison. We should picture a dynamic confinement, a system full of exchange and motion, where separation becomes creation rather than release. The strong interaction is severe, yes, but it is also productive. It is what gives the proton its integrity, its mass structure, its persistence. It is the reason the crowded heart of matter remains crowded instead of dissolving into incoherence. And once you begin thinking of the proton this way, as a place where quarks are held not by quiet walls but by ceaseless gluon activity, another question naturally starts to creep in. If this force is always at work, if quarks are always interacting, always exchanging, always confined in motion, then what exactly are they doing from one moment to the next when, from the outside, the proton appears to be sitting there doing absolutely nothing at all? If the proton looks simple from the outside, that simplicity would be one of the most successful disguises in all of physics. From a comfortable distance, it behaves like a stable particle with a definite mass, a definite electric charge, and a dependable role in the structure of atoms. It is the sort of thing you could almost mistake for a basic unit, a neat little brick in the wall of matter. But the closer physicists have looked, the less the proton has resembled a brick, and the more it has resembled a busy interior with no real silence in it at all. That busyness does not stop with the valence quarks and the gluons that bind them. In fact, once you move beyond the first tidy picture, you discover something even stranger. Beneath the simple description of 2 up quarks and 1 down quark lies a restless sea of temporary activity, a continuous quantum background in which extra quark and antiquark pairs can appear and disappear, gluons split and recombine, and the whole proton becomes less like a container with contents and more like an ongoing event. The word sea is used for good reason. It suggests something more fluid than a list. A list says these are the things inside. A sea says conditions are changing all the time. There is motion, exchange, rising and sinking, brief appearances, hidden currents. And the proton, once you begin to think in these terms, starts to feel less like a tidy package and more like weather under pressure. Stable weather, if such a thing can be said with a straight face, but weather all the same. This idea can be difficult at first because we instinctively want to separate the real from the temporary. We like categories with firm edges, permanent things on one side, fleeting things on the other. The proton, however, does not care much for our preference. Its identity is stable, yes, but its interior includes contributions from entities that do not sit there forever in the way a bolt sits in a machine. The C quarks, as they are called, are not part of the proton in the simple bookkeeping sense that the valence quarks are. If you ask what gives the proton its defining quark content, the answer remains 2 up quarks and 1 down quark. But if you ask what is physically going on inside the proton at any given moment, the answer is much more crowded. A gluon inside the proton can briefly give rise to a quark and an antiquark pair. Those two may exist only fleetingly before annihilating again or before their influence is absorbed back into the larger internal dynamics. Yet while they are there, even briefly, they matter. They contribute to the full quantum description of the proton. They affect how momentum is distributed. They influence the results of scattering experiments. They are not just decorative detail. They are part of the reason the proton is richer than the earliest diagrams ever suggested. There is something almost mischievous about this from a human point of view. We finally accept that the proton is not elementary, and we learn that it contains quarks. Then, just as we're about to feel pleased with ourselves, and perhaps make a cup of tea in celebration, physics leans in and says yes, but also the inside is full of temporary extras and the force carriers are doing half the work and the vacuum is not really empty either. The universe has a way of granting understanding only by making the understood thing more complicated than before. To see why this restless sea appears, we need to remember that the proton is not built from tiny billiard balls but from quantum fields. That phrase can sound forbidding, but the basic idea is not so terrible. In modern physics, particles are not best thought of as little pellets detached from everything else. They are excitations of underlying fields. Those fields can fluctuate, interact, and produce what we observe as particles. Empty space, in this view, is not an inert blank. It is more like a stage that never fully settles, even when the lights seem low and the actors appear to have gone home. Within the proton, the fields associated with quarks and gluons are particularly energetic and tightly engaged. The strong interaction is active there all the time. Gluons are exchanged continuously, and because gluons themselves participate in the dynamics, they can give rise to further activity. This includes the appearance of quark and antiquark pairs from the available energy, so the proton is not just 3 quarks plus some glue. It is a dense quantum environment in which the very distinction between constituent and background begins to blur. This matters because a proton is not measured by peering quietly at a frozen interior. It is measured through interactions, especially collisions. When high-energy electrons are fired at protons, the scattering patterns reveal how the proton responds at different resolutions, and resolution is crucial here. At a coarse level, the proton may look simpler. At a finer level, more structure emerges. It is a bit like looking at the surface of the sea from a clifftop and seeing a calm blue sheet, only to climb down and discover waves, foam, riptides, drifting weed, bubbles, and the occasional alarming gull. The closer you look, the more the stillness turns out to have been a matter of distance. In those scattering experiments, one of the great revelations was that the proton contains many more effective participants than just the 3 valence quarks. These participants are often called partons in the experimental language, because at high energy, the proton seems to present a whole collection of momentum-carrying constituents to the incoming probe. Some of those are the valence quarks, many are gluons, some arise from the sea. The deeper one looks, the more crowded the picture becomes. This is an important correction to the casual phrase, what is inside a proton. The answer depends partly on how you ask and how hard you look. At one scale, the proton can be summarized by its valence quarks. At another, it is a teeming quantum system full of gluonic activity and short-lived pairs. Both descriptions are true in their proper context. Physics often works this way. It does not give one single picture that is useful at every scale. It gives layered descriptions, each revealing new detail as the probing becomes more refined. And what a peculiar detail it is. Imagine trying to explain to someone with no background in the subject that a particle can be defined by 3 quarks, and yet constantly contain more than 3 quarks in a meaningful sense. It sounds contradictory until you understand that the extra pairs come with matching antiquarks, so they do not alter the net defining content. The proton remains a proton because the valence structure is unchanged. The C is extra activity layered on top of that stable identity. It is not a change of species, it is part of the species being itself. That distinction becomes easier if you compare it cautiously to a company payroll and the daily traffic in and out of the building. The permanent staff determine what sort of company it is, but the building may also be full of temporary visitors, deliveries, maintenance crews, and people who appear very briefly, confuse everyone, and disappear before lunch. The company remains the same company, but the actual life inside it at any moment is much busier than the official staff list would suggest. The analogy is imperfect, as all analogies are, but it gets across the difference between defining content and temporary participation. There is another surprising feature here. The C is not a minor afterthought tucked quietly behind the main action. Gluons, in particular, carry a large fraction of the proton momentum. This means that much of what the proton is doing internally depends on entities that are not part of the simple 3-quark picture in the ordinary popular sense. If you asked where the proton momentum lives, the answer would force you to look well beyond the valence quarks. The proton is not just held together by gluons, it is dynamically shaped by them. And because gluons can generate quark and antiquark pairs, the C becomes deeply tied to the gluonic structure. One might be tempted to imagine the proton as having a solid little centre and a sort of decorative mist around it. That would be far too neat. The C is woven into the proton interior. It is part of the restless pattern through which the proton exists as a stable bound state. Without the C and the gluon activity, the true quantum life of the proton would be missing. This brings us to a quiet but important change in mindset. The everyday word inside tends to suggest a passive interior, as if there were a boundary and then a place where things are stored. But the proton is not storing its contents like a cupboard. Its interior is an active balance of fields and interactions. The C beneath the surface is not beneath in the sense of a lower layer resting peacefully under a crust. It is beneath only in the sense that it is hidden from the simplest first description. Once you uncover it, you realize there was never a simple dry floor underneath. There was only more motion. Physicists have even learned that the C is not always perfectly balanced in the naive way one might first expect. At one time, it seemed reasonable to imagine that if gluons create quark and antiquark pairs, then certain types should appear symmetrically. But experiments have revealed asymmetries in the C. For instance, the balance between some light antiquarks is not exactly even. That might sound like a tiny detail, but it is exactly the kind of detail that tells you the proton is not merely a bland statistical soup. Its internal structure has character. It has patterns that reflect the deeper dynamics of the strong interaction and the ways quarks and gluons arrange themselves in a bound state. Even the proton spin problem touches this territory. Physicists once hoped that the proton spin would be accounted for mostly by the valence quark spins. Instead, the story turned out to involve gluons, orbital motion, and the broader internal dynamics, including C contributions. Once again, the C beneath the surface refuses to stay politely hidden. It keeps showing up in the properties we measure from the outside. There is something rather beautiful about that. The proton looks simple from afar, but its apparent simplicity is the outward face of an internal argument. The observable properties emerge from a negotiation among quarks, gluons, and fluctuations. The stable visible world is supported by hidden instability that does not destroy structure, but sustains it. This is one of nature's favourite moves. What looks solid is often the result of activity too quick or too small for direct human sense to register. You can find versions of that idea all across physics. Temperature is microscopic motion described in bulk. Pressure is countless collisions summarized by one tidy number. A note from a violin string feels like a single sound, but it is really a structured vibration rich with harmonics. The proton belongs to this tradition of deceptive simplicity. It is one particle, yes, but also an organised storm at small scales. And because it is quantum, one has to be careful not to imagine the sea as little objects popping in and out, like fish breaching in clear sunlight. The language of temporary particles is useful, but it's still a language for field behaviour and quantum processes, not a tiny cartoon film literally running inside the proton. The sea is real in its effects, but it is not a miniature aquarium. It is part of the mathematical and physical structure by which the proton behaves in experiments and carries its properties. This is where science often asks us to become a little more mature in our imagination. Childish imagination wants pictures with edges and moving pieces. Mature imagination can tolerate entities that are best understood through patterns of interaction, rather than neat visual scenes. That does not make the subject cold. If anything, it makes it more interesting. The proton is not less real because we cannot sketch its inner life like the inside of a clock. It is more subtle, and therefore more revealing of what the universe is actually like, rather than what our furniture trained us to expect. It is also worth noticing how much of this story depends on energy. The sea is not an optional extra laid on top of the proton from outside. It emerges from the intense field activity and the possibility, within quantum theory, for energy to participate in particle creation and annihilation. In a sense, the proton is rich enough inside to keep making brief new structure from its own internal life. That is one reason why the old idea of matter as merely stuff becomes less and less adequate the deeper you go. Matter at this scale is not just substance, it is activity constrained into persistence. The same insight helps explain why the proton mass is not simply a matter of adding up the masses of a few quarks. Much of the proton mass comes from the energy of confinement and internal dynamics. The sea and the gluons are not irrelevant to that broader picture. They are part of the energetic content through which the proton becomes the thing it is. So even the weight of ordinary matter owes something to this hidden turbulence. The table, the tree, the bone, the book, all of them inherit part of their mass from a microscopic interior that is far less quiet than their surfaces suggest. And yet, for all this inner unrest, the proton does not fall apart. That is perhaps the most astonishing thing about it. It remains stable, it contributes to atoms that can last for billions of years. It anchors nuclei, chemistry, planets, bodies. The sea beneath the surface does not signal weakness, it signals depth. Stability here is not the absence of motion, it is the successful organisation of motion. By now, the old picture of the proton as three little quarks in a small box should feel much too thin for the job. What we actually have is a bound state with defining valence quarks, a significant gluon population, and a sea of temporary quark and antiquark pairs that participate in the proton's full identity as revealed by experiment. The proton is not hollow, not static, and not finished once you have named its three main quarks. Beneath the first tidy summary lies a second level of description, and beneath that perhaps an even deeper question. Because once we admit that the proton has no truly quiet interior, once we accept that even its supposed contents are mixed with field activity and temporary emergence, we are pushed toward a more unsettling thought. Perhaps the real question is no longer what sits inside the proton, but what sort of thing a quark itself is if the world around it is already this restless, and whether a quark has anything like a surface or an interior at all when we finally turn our attention directly toward it. That question sounds simple enough when said quickly, and that is part of what makes it so slippery. Do quarks even have an inside? At first glance, the answer feels like it ought to be straightforward. Large things have insides. A suitcase has shirts inside. A loaf has a softer middle. A watch has gears tucked under the case, assuming no one in the household has already taken it apart with misplaced confidence and a butter knife. So surely if a proton has things inside it, and those things are quarks, then a quark should also have something inside it. Smaller gears, perhaps, tinier ingredients, a deeper layer waiting patiently for us to notice. But physics does not always reward that kind of reasonable-sounding assumption. In fact, one of the most unsettling habits of modern physics is that it keeps forcing us to examine not just the answers to our questions, but the shape of the questions themselves. And this is one of those cases. When we ask what is inside a quark, we're already assuming that a quark is the kind of thing that has an inside in the ordinary spatial sense. We are assuming it has an outer boundary, an interior region, and some further structure enclosed within that region. That may be a very natural assumption for minds that evolved around fruit, furniture, teacups, and doors, but nature at very small scales does not always agree to think in household terms. According to the best theory we currently have for ordinary matter and its fundamental ingredients, quarks are elementary particles. That word elementary does important work. It does not mean tiny in the way a crumb is tiny compared with a loaf. It means that, as far as present evidence goes, quarks do not appear to be made of smaller constituents. They are not thought of as little composite bundles the way protons and neutrons are. They are treated instead as fundamental excitations of quark fields. That phrasing can sound remote if one is not used to it, but the basic point is simple. In the current framework, quarks are not little bags of smaller objects. They are among the base-level ingredients the theory starts with. Now, whenever physicists say something is elementary, they are usually trying to sound careful rather than triumphant. Science has been embarrassed before by confident declarations of finality. Atoms were once supposed to be indivisible, their nuclei looked fundamental, then protons and neutrons looked promising. Each time the story turned out to have another layer. So when modern physics treats quarks as elementary, it does not mean the matter is closed forever and the universe has signed the paperwork. It means that all experiments so far are consistent with quarks having no detectable internal structure. That last part is the heart of it. No detectable internal structure. It is possible in principle that quarks are made of something deeper. People have speculated about such possibilities. There have been ideas involving more fundamental ingredients beneath quarks, sometimes given names that sound as though they were invented during a late evening by someone very determined not to go home yet. But none of those ideas has been confirmed. No experiment has forced us to conclude that quarks are composite. No hidden interior has shown itself clearly in the data. So for now, quarks are treated as point-like in the sense that they show no measurable size or substructure at the resolutions we can probe. That phrase point-like is one of those technical words that can mislead if taken too literally. It does not mean a quark is a tiny hard dot, with the shape of a mathematical point in the childish cartoon sense. It means that in experiments designed to reveal structure, quarks behave as though they have no internal parts. If an object has internal structure, you can often detect it by hitting it hard enough, or probing it with enough precision, and seeing departures from the behavior expected of a structureless particle. That is how physicists learned that protons and neutrons were not elementary. High-energy scattering experiments revealed substructure. Incoming particles bounced off internal constituents in ways that gave the game away. The proton was not a smooth, indivisible thing after all. If quarks had a similar hidden structure, we would expect signs of it. We might see evidence that their interactions change in a way that reveals deeper parts. We might see excited versions of quarks, rather like how atoms have excited states, or how composite systems often show extra internal modes. We might see deviations in very high-energy collisions suggesting that quarks are not truly elementary, but are built from smaller objects bound together. So far, none of that has appeared in a decisive way. The data keep treating quarks like fundamental actors. There is an odd kind of frustration in that, because human curiosity tends to assume that one more layer must always be waiting. We're suspicious of the bottom rung. Tell us that a thing has no inside, and we are immediately tempted to ask whether that only means we have not looked hard enough. Very often in science that suspicion has been productive. It led us beyond atoms, beyond nuclei, beyond protons and neutrons. But suspicion can become habit, and habit can become expectation, and expectation is not evidence. At some point, the universe may simply stop offering deeper nested boxes of the kind we're used to opening. Or perhaps it will not. Perhaps quarks are composite after all, and we just have not reached the scale where the cracks show. The honest answer is that we do not know. But there is a crucial difference between not knowing and having evidence. Right now, we do not have evidence that quarks possess an inside in the way composite particles do. Part of the confusion comes from everyday language. The word inside implies space arranged in a familiar way. It implies that the object occupies some region, and that within that region there is more detail to uncover. That works beautifully for an orange, passably for a watch, and not at all reliably for a fundamental particle in quantum field theory. A quark is not a tiny orange. It is not even a tiny bead. It is something that enters the theory as a basic excitation with certain properties, such as mass, electric charge, colour charge, spin, and flavour. Those properties can be measured and inferred through interactions, but they do not require the quark to be built like a miniature machine. This is where the imagination has to mature a little. We spend most of childhood learning that objects can be taken apart. We spend much of adulthood learning that not every useful question is a taking apart question. Sometimes the better question is not what smaller thing is inside this, but what role does this thing play, what properties does it have, how does it interact, and what evidence would count against our present description of it. Physics at small scales is often less about literal miniature anatomy, and more about the behaviour of fields, symmetries, and interactions. Consider the electron for a moment. The electron is also treated as elementary in the standard framework. People do not usually ask what is inside an electron with the same determination they reserve for quarks, perhaps because quarks sound more mysterious, and because quarks are already hidden inside familiar particles. But the electron presents the same kind of conceptual challenge. Does it have a size? Does it have internal moving parts? All current evidence says no detectable internal structure. It behaves as a fundamental particle in the theory. The quark stands in that same category, though with the additional complication that it cannot be observed in isolation under ordinary conditions because of confinement. That confinement sometimes tempts people into thinking quarks must have an inside simply because they are trapped. One imagines something being hidden behind the confinement, like a person staying indoors because the weather is dreadful. But confinement does not imply internal structure. It tells us about the strong interaction and the way quarks behave collectively inside hadrons. It tells us that quarks are not free in the everyday world. It does not tell us that a quark itself contains smaller pieces. In fact, one of the more subtle possibilities is that the idea of an inside may be the wrong kind of question altogether for a truly elementary particle. Asking what happens inside a quark may be a bit like asking what country is inside the number 3. The problem is not that the answer is difficult. The problem is that the grammar of the question quietly misfires. It takes a concept suited to one category of thing and applies it to another category where it may not belong. That is not to say the question is foolish. It is an extremely useful question because it forces us to clarify what sort of thing a quark is supposed to be. But its usefulness may lie more in the clarification than in any hidden interior it reveals. Of course, physics does not simply declare a question invalid because it feels awkward. It tests, it probes, it hurls particles at particles with extravagant dedication and waits to see whether reality keeps its story straight. This is how the idea of quark compositeness is constrained. If quarks had structure, very high energy collisions would likely begin to show anomalies. The patterns of scattering would shift. The probabilities of certain interactions would wander away from the predictions of a structureless quark picture. So far, the standard description has held up remarkably well. That does not prove there is no deeper layer. Science is rarely in the business of absolute metaphysical proof, but it does mean that if there is an inside, it is hiding below scales we have not yet reached. That leads to an interesting change in tone. The question then becomes not do quarks have an inside in the everyday sense, but how small a scale have we probed without seeing evidence of one? Physics often works in exactly that cautious way. It marks the frontier. Up to here, no substructure. Beyond here, unknown. This is less satisfying to the dramatic part of the mind, but much more faithful to how science actually proceeds. There is also a theoretical reason many physicists are content, at least provisionally, to treat quarks as elementary. The standard model of particle physics is astonishingly successful. It organises quarks, leptons, force carriers, and their interactions into a framework that has survived decades of experimental testing. Quarks fit naturally into that framework as basic ingredients. The theory does not need them to have smaller constituents in order to account for the phenomena we observe. Now, not needing a deeper layer is not the same as proving one does not exist. But in science, unnecessary extra layers are treated with suspicion until the evidence demands them. This is one reason speculative subquark theories have remained speculative. They are not impossible, they are simply unsupported. One can invent smaller building blocks beneath quarks, but once you do that, you must explain why quarks behave so point-like, why the deeper structure leaves so little trace, why the standard model works as well as it does, and what new predictions your theory makes that can actually be tested. It is not enough to say perhaps there is more. Science replies yes, perhaps, but show your work. That may sound stern, but it is a healthy sternness. Without it, physics would become a hobby of infinite nesting dolls with no discipline about where evidence ends and imagination begins. Imagination is essential. It drives questions, models, and bold proposals. But evidence is what prevents the subject from drifting into decorative mythology. And on the matter of quark interiors, the evidence remains stubbornly plain. No confirmed sign of internal structure. There is another subtlety worth holding on to. Even if quarks are elementary, that does not mean they are featureless in every meaningful sense. A quark has properties. It has charge. It has mass. It has spin. It has colour charge. It belongs to a flavour category. It participates in the weak interaction, which can change one flavour into another under the right conditions. So a quark is not a blank nothing. It is rich in the sense that it carries a package of physical traits. What it seems not to be, at least as far as we can presently tell, is a composite object with smaller moving parts inside. This distinction matters because people often confuse being elementary with being trivial. An elementary particle is not trivial. It is simply not built from smaller known constituents. The proton is composite and dynamic. The quark, as currently understood, is elementary and still fully involved in the drama of the forces around it. It is not boring merely because it lacks a known interior. Quite the opposite. Quarks are strange enough without requiring extra furniture inside them, and yet the temptation remains to ask whether Pointlike truly means dimensionless in some final physical sense. Here again one has to tread carefully. In quantum field theory, particles are treated in a way that does not map neatly onto everyday geometry. A quark is associated with a field. When we talk about local interactions, we are describing behaviour that occurs as though the particle has no extended substructure at the scale in question. But the notion of size at the smallest scales can become tangled with the limits of measurement, quantum uncertainty, and the very language we use to describe fields. So even the statement quarks are point-like is not a cartoon statement. It is a statement about how they behave in experiments and in the theory. That can feel frustrating to anyone who wants a nice visual answer. Are quarks tiny balls? No. Are they mathematical points? Not in the naive schoolbook sense. Are they elementary excitations with no observed internal structure? Yes, that is the best current description. Science, rather often, answers by taking away the picture you wanted and replacing it with a more careful sentence. Still, there is room here for wonder rather than disappointment. It is extraordinary that the visible world may rest partly on entities that have no inside in the familiar sense. It means the hierarchy of matter might not continue forever as nested lumps. It means that at some level the world may be built not from smaller and smaller objects of the same kind, but from fundamental ingredients that only make sense through their properties and interactions. That is a more abstract view than ordinary intuition likes, but it may be closer to the truth. One can even see this as a kind of humility lesson built into physics. We begin with the assumption that the universe will resemble our habits of thought if we shrink it enough. It does not. We expect surfaces, interiors, little structures within larger structures, all the way down. Instead, we get fields, symmetries, confinement, quantum behavior, and entities that may be fundamental not because we lack imagination, but because that is simply how the world is organized. Or perhaps it is not. That possibility remains open, and it keeps the question alive in a healthy way. Future experiments may yet reveal departures from the standard picture. Higher energies may uncover compositeness, excited quark states, or some new layer beneath the current framework. Physics has surprised itself before, and will likely do so again. The proper attitude is neither smug finality nor endless suspicion, but disciplined curiosity. For now, quarks do not seem to have an inside. Tomorrow, the evidence may still say the same, or it may not. And there is one more twist. Even if quarks do not have an inside, the question has not been wasted. By asking it, we are forced to sharpen our picture of matter. We are forced to distinguish composite from elementary, picture from evidence, container language from field language. We are forced to notice that what happens around quarks inside protons is not the same as what would happen inside a quark itself. In other words, the question teaches us something even if the answer is mostly no, not in the way you mean. That sort of answer can feel unsatisfying at first, but it opens a new door almost immediately. If quarks are elementary, then their individuality does not come from hidden internal machinery. It comes from their observable properties, from the strange labels and rules that distinguish one kind from another. And that means the next step is not to keep rummaging for smaller pieces inside them, but to ask why quarks come in different varieties at all, and what on earth physicists mean when they say quarks have flavors and colors, even though none of them taste of anything, and none of them, so far as anyone can tell, is actually blue. That brings us to one of the most peculiar naming decisions in all of physics, because once you start talking about quarks seriously, you very quickly run into the claim that quarks have color. This is usually the point where a perfectly reasonable person pauses and wonders whether the scientists involved had been working too late, had run out of dignified language, or had simply decided to see how much nonsense the rest of us would tolerate before asking for clarification. The answer, as is so often the case, is that the name is odd, the idea is real, and the truth is much more precise than the word first suggests. Quarks do not have colour in the ordinary visual sense. They are not tiny red specks or faintly green pellets, or moody blue crumbs of matter floating around inside protons. Nobody has ever peered into a detector and announced that the up quark appeared especially turquoise today. The names red, green, and blue are labels for a property called colour charge, and that property is what allows quarks to participate in the strong interaction. It is a bookkeeping language, but it is not a childish one. It is part of the mathematical structure of the theory, and without it the behaviour of quarks and gluons would make much less sense. Now the need for this extra property arose because physicists found that the simple quark picture was not quite enough on its own. Quarks could be used to classify hadrons very successfully, but when people tried to build certain particles out of quarks, awkward questions appeared. There were states that seemed to require multiple quarks of the same type, sitting in arrangements that, under ordinary quantum rules, looked suspicious. Fermions, which include quarks and electrons, do not like being piled into the exact same quantum state. They are not sociable in that particular way. If quarks were distinguished only by flavour, spin, and the other obvious labels, some particles would have looked impossible or at least badly behaved. Colour charge solved that problem beautifully. It gave quarks an additional degree of freedom, a way for quarks that are otherwise similar to differ from one another in a physically meaningful way. More than that, it became the foundation of the whole theory of the strong force. Once colour was introduced, quarks could combine in the right patterns, the observed particles could be described consistently, and the strange behaviour of the strong interaction began to settle into a coherent framework. The basic idea is that quarks come in 3 colour charges, called red, green, and blue. Antiquarks come with corresponding anticolours. These names are not arbitrary in the sense of being random, but they are chosen partly because 3 colours can combine to make a balanced whole in a familiar visual analogy. Again, this is not literal colour mixing. It is simply a convenient way to remember that the combinations of quarks which produce ordinary observed particles must end up colour neutral overall. A proton, for instance, contains 3 quarks, and those 3 quarks together form a colourless combination. A meson contains a quark and an antiquark, and those two together also form a colourless combination. The strong interaction, in the stable particles we actually observe directly, seems to insist on this kind of neutrality. That word colourless can also mislead if taken too literally, so it is worth pausing over it. Colourless does not mean invisible or pale or washed out. It means neutral with respect to colour charge. Just as an electrically neutral object has a balance of positive and negative charge, a colour-neutral hadron has a combination of colour charges that cancels appropriately. The proton may be full of quarks and gluons, but as a whole it does not carry net colour charge into the outside world. That is one reason why we do not experience the strong force in the same everyday way we experience electric effects. The colour charge is confined inside hadrons in a very specific manner. And now we arrive at the other major character in this story, the gluon. The gluon is the carrier of the strong force, rather as the photon is the carrier of the electromagnetic force. That comparison is useful at first, but it very quickly becomes incomplete because gluons behave in a way photons do not. A photon does not carry electric charge, so photons do not ordinarily interact strongly with each other. Gluons are different. Gluons carry colour charge themselves. This means that the particles carrying the strong interaction are also participants in it. They can interact with quarks, of course, but they can also interact with other gluons. This feature changes everything. It makes the strong interaction far more tangled, far more self-involved, and far more difficult to simplify into a clean picture. The gluon field is not just a neutral messenger service, calmly delivering force from one quark to another, and then going home. It is a network in which the messengers are also caught up in the message. They contribute to the structure, the confinement, the momentum distribution, and much of the mass of hadrons. In the proton, gluons are not just holding quarks together from the sidelines. They are part of the very substance of what the proton is doing. This is one reason the strong force behaves so differently from electromagnetism. With electric charge, opposites attract and like charges repel, and the force weakens with distance in a relatively straightforward way. The strong force is more subtle. At very short distances, quarks behave as though they are less strongly bound. This is the phenomenon called asymptotic freedom, and it is one of the most important discoveries in modern particle physics. It means that when quarks are pushed very close together, such as in the extremely energetic interior conditions probed during high-energy collisions, they interact more weakly than one might expect from something called the strong force. That sounds backwards at first, but it is true. Very close up, quarks are comparatively freer, and yet try to pull quarks apart, and the opposite happens. The force does not simply fade away the way gravity or electric attraction would. Instead, the interaction grows stronger with increasing separation. The field between quarks stores more and more energy. At some point, instead of giving you an isolated quark, the system finds it easier to create a new quark and antiquark pair from the energy you've poured in. The result is not one freed quark, but new colour-neutral particles. This is confinement again, but now seen through the lens of colour charge. Quarks are bound because colour charge and gluon dynamics produce a force law that does not allow the easy escape we might expect from familiar forces. One of the most helpful ways to think about this is to remember that colour charge is not just another kind of plus and minus. If it were that simple, the strong force would behave far more like electromagnetism. Instead, with 3 colours and the way gluons carry colour themselves, the field structure becomes richer and more elaborate. The energy does not spread out in the same forgiving way. It becomes concentrated in something more like a narrow connection between quarks, often described as a flux tube in more technical discussions. Stretch that connection, and you do not thin it out harmlessly. You build tension in it, pull hard enough, and the system pays for new particle creation rather than allowing a clean colour-charged object to wander free. This is a remarkable rule. It means that the visible matter in the world is built from ingredients that are never directly found on their own. Quarks help form protons and neutrons, and those in turn form nuclei, atoms, molecules, tables, lungs, biscuits, and bad office coffee. But the quarks themselves remain hidden behind confinement. Their colour charges never show up naked in the world around us. What we observe are colour-neutral combinations. Nature at this level is oddly strict about presentation. There is something almost social about it, though perhaps one should be careful not to take that too far. Quarks may carry colour, but no hadron is allowed to stroll into the world wearing its colours openly. Everything that survives as a free particle under ordinary conditions must be properly colour neutral before it leaves the building. One imagines the strong force as an unusually stern doorman with very specific dress code requirements. Of course, the theory underlying all of this, quantum chromodynamics, is much more than a collection of amusing labels. It is one of the core pieces of the standard model, and it has been tested with enormous success. It explains the behaviour of quarks and gluons, the existence of confinement, the phenomenon of asymptotic freedom, and the internal complexity of hadrons. But it's not an easy theory to solve in the regime where the binding is strongest. This is where the mathematics becomes serious in a way that tends to frighten casual visitors and overexcite certain specialists. The equations are clear enough in principle, yet the consequences for bound states like protons and neutrons are complicated enough that physicists often rely on sophisticated computational methods to work them out in detail. That difficulty is not a sign of failure. It is a sign that the strong interaction is exactly what it claims to be: strong, non-linear, and internally tangled. The fact that we understand the rules and still have to work very hard to calculate the consequences is simply part of doing physics in a world that does not always simplify itself for our convenience. It would be nice, perhaps, if the proton were held together by something more orderly and better behaved. But the universe has never shown much concern for what would be nice. There is another subtle point here that often gets missed in simpler explanations. Colour charge is not just about binding quarks into fixed little groups. It also shapes the whole dynamic interior of hadrons. Because gluons carry colour, they contribute heavily to the proton's internal momentum and energy. They can split into quark-antiquark pairs, feeding the sea of temporary activity inside the proton. They influence the distribution of spin and mass. So colour charge is not a decorative label tacked onto quarks so the equations work out. It is the property that underlies the restless inner life we have already been discussing. And that inner life has consequences well beyond the small-scale world of detectors and theory papers. The very stability of atomic nuclei depends indirectly on these rules. If colour charge did not behave this way, if the strong interaction were weaker or more easily diluted with distance, protons and neutrons might not form as they do. If they did not form, nuclei would not either. Without nuclei, atoms in the familiar sense would vanish from the story before it even got started. The chemistry of life, the formation of planets, the existence of stars built from ordinary matter, all of that depends on the peculiar rules of the strong interaction. So when physicists talk about colour charge, they are not discussing some obscure decorative feature of particle theory. They are discussing one of the conditions that allows the visible universe to exist in its present form. This can feel strange because colour charge has no obvious analogue in daily life. Electric charge at least has a certain intuitive foothold. We can experience static electricity. We know magnets do odd things on a fridge. Gravity needs almost no introduction because it has been dropping objects on people for the full length of human history. Colour charge is more hidden. It never announces itself in the kitchen or the garden. Its effects are locked away in hadrons and nuclei, and yet it is one of the most important properties in the material world. The deeper you go into physics, the more often you meet things like this: fundamental rules with enormous consequences and absolutely dreadful public relations. There is also a deeper intellectual lesson tucked away here. At large scales, we are trained to think of forces as acting between already existing objects. One billiard ball hits another, one magnet pulls a nail. Gravity acts between the Earth and the Moon, but colour charge forces us to see that, at smaller scales, the force and the object are more deeply intertwined. A proton is not merely a box containing quarks that happen to feel a force. The proton exists as the bound state that it is because of colour charge and gluon dynamics. Remove those rules, and the proton is not the proton anymore. The force is not something externally applied to a finished object. It is part of what the object fundamentally is. This makes the strong force feel less like a background influence, and more like an architectural principle. It does not merely hold a completed structure together. It creates the possibility of the structure in the first place. That is why the distinction between quarks and gluons, while real and important, does not line up neatly with the distinction between contents and glue in the everyday sense. Quarks are the defining valence ingredients, yes, but gluons are inseparable from the whole internal reality. The strange rules of the strong force do not just supervise the proton, they make it possible. And once you start to view the proton this way, as a colour-neutral knot of quarks and gluons living under rules unlike anything in ordinary intuition, another issue naturally starts to surface. If colour charge explains why quarks are confined, and if the strong force becomes weaker at very short distances but stronger as quarks are pulled apart, then how exactly did physicists learn any of this in the first place, given that the relevant processes happen far beyond direct human sight, and the objects involved refuse to step out alone for inspection? To understand the inside of matter, physicists had to accept a slightly awkward fact. At the scales where quarks and gluons matter, you do not get very far by simply looking harder. A normal microscope is useless long before you reach the atom. Even the cleverest microscope based on light runs into trouble, because light itself has a limit as a probing tool. If the wavelength is too large, it cannot resolve tiny details. Trying to inspect a proton with ordinary visible light would be like trying to map the shape of a grain of sand using beach waves. You may get a general sense that something is there, but the details will remain politely out of reach. So physics did what it often does when gentle methods fail. It started throwing things at other things very fast and measuring the wreckage with extraordinary patience. That may sound crude, and in a sense it is, but it is also one of the most refined techniques ever invented. Particle physics is sometimes described as a science of smashing, which is true in the way that surgery is a matter of cutting things open. The rough description is not wrong, but it leaves out the precision, the purpose, and the years of thought needed to make sense of what the cutting reveals. When physicists accelerate particles to enormous speeds and let them collide, they are not simply making tiny messes for the fun of it, though one suspects that for some of them the fun is real. They are probing structure. They are asking nature what lies inside matter by forcing matter to respond under conditions far beyond ordinary life. This basic logic goes back a long way. One of the great turning points in the history of physics came when Ernest Rutherford and his collaborators studied how alpha particles scattered off thin metal foil. That experiment is often remembered in school as the one that discovered the atomic nucleus, and for once school is not exaggerating. Most of the incoming particles passed through with little deflection, but a few bounced back sharply, which made sense only if the atom contained a tiny dense centre. In other words, By firing one thing at another and observing the angles and outcomes, physicists learned that the atom was not a smooth blob. It had internal structure. That same strategy was later extended to smaller scales. If you want to know whether the proton is elementary or composite, you do not ask it politely. You hit it with something that can resolve fine detail, and you watch what happens. The harder the hit, the finer the detail you can probe. High energy means short wavelength in the quantum sense, and short wavelength means better resolving power. This is one of those cases where violence and precision turn out to be close cousins. The more energetic the probe, the smaller the structures it can meaningfully investigate. By the middle of the 20th century, physicists had accelerators capable of doing exactly this. They could fire electrons at protons with enough energy that the collisions were no longer just mild nudges. They became deep probes of the proton interior. Electrons were especially useful for this because they do not participate in the strong interaction the way quarks do. That makes them cleaner probes in certain experiments. They interact electromagnetically, which means they can pass in, scatter, and reveal information without immediately getting tangled in the full chaos of the strong force in the way a hadronic probe might. This is where the famous deep inelastic scattering experiments entered the story. The name sounds severe, but the idea is fairly clear once you unpack it. Scattering means one particle hits another and changes direction. Inelastic means the target does not remain unchanged. The collision transfers enough energy to disrupt the original state, so the proton can break apart or be transformed into a spray of other particles. Deep means the probe reaches into the small-scale structure, rather than merely glancing off the outside. In other words, these were energetic collisions designed to expose whether the proton had smaller components hidden within it, and the answer came back yes. When high-energy electrons were fired at protons, the scattering patterns did not behave as though the proton were a single smooth object. They behaved as though the electron was hit in smaller, more localized constituents inside. The data were consistent with the presence of point-like charged particles within the proton. This was a huge result. It gave powerful experimental support to the idea that protons contain quarks. At that point, quarks were no longer just neat theoretical bookkeeping devices. They were becoming physically unavoidable. It is worth pausing over how strange that process really is. Nobody opened a proton and looked in with a lens. Nobody saw a tiny trio sitting there with labels attached. Instead, physicists inferred the presence of quarks from patterns in scattering data, from distributions of angles and energies, from the way the outgoing particles behaved after violent collisions. This is one of the deeper lessons of modern science. We often know things not by directly viewing them in a naive sense, but by learning the signature they leave in carefully designed experiments. Reality does not always present itself as a picture. Sometimes it presents itself as a statistical pattern that only becomes meaningful when theory and experiment meet. The proton, in these collisions, was revealed not as a featureless sphere but as something more structured. Yet even then, the story did not settle into a simple one. The quarks that showed up in the experiments seemed to behave in a way that fit beautifully with the idea of asymptotic freedom. At very short distances and very high energies, they acted almost as if they were more independent. That was a remarkable clue. It suggested that the strong force becomes weaker at very short range, allowing the probe to strike something that looks nearly free during the brief instant of the collision. This was exactly the sort of behaviour that quantum chromodynamics would later explain with great success. So high-energy collisions gave physicists a very odd combination of truths. On the one hand, quarks are confined and never observed drifting around alone under normal conditions. On the other hand, inside a proton, during a sufficiently energetic collision, they can behave as though they are individual scattering centres. That sounds contradictory only if one imagines the proton as a little container with permanent conditions. In reality, the way a system responds depends on how it is probed. Strike it hard enough and briefly enough, and the structure can reveal itself in ways not visible at lower energies. The proton, however, had more surprises in store. Early simple quark models might have led one to expect that most of the proton momentum would be carried by the valence quarks. After all, those are the defining constituents. Yet the experiments showed a more complicated picture. The momentum distribution did not fit a story in which only 3 quarks were doing all the work. A large portion of the proton momentum had to be carried by something else, and that something else was largely the gluons. So even the experiments that helped confirm quarks also deepen the mystery by showing that the proton interior is full of more than just its 3 main residents. This is one reason why the language of partons became useful. In the context of very high energy collisions, physicists often speak of the proton as containing partons, meaning the effective constituents that the incoming probe seems to scatter from. Some of those partons are valence quarks, many are gluons, others reflect the sea of temporary quark and antiquark pairs. The Parton picture was a practical way of describing what the experiments seemed to reveal before the full modern understanding of quantum chromodynamics had settled into place. It was a kind of experimental honesty. We can tell there are smaller momentum-carrying bits inside, the language said, even if the deeper theoretical picture is still being worked out. And that, in science, is often how progress actually looks. Not a perfect theory descending from the heavens in one piece, but a sequence of increasingly accurate descriptions, each pushed forward by data that refused to fit the old picture. The proton was first thought simple, then discovered to be composite, then found to be more complicated inside than the first composite picture allowed. Physics rarely rewards us with a final answer that stays tidy for long. Colliders later took this strategy much further. Instead of merely firing a beam at a fixed target, physicists built machines in which 2 beams of particles race toward one another and collide head-on. This is a much more efficient way to concentrate energy in the impact itself. If you fire a fast particle at a stationary target, part of the energy goes into the motion of the debris as a whole. If 2 equally energetic beams meet head-on, much more of the energy becomes available for new particle production, and for probing fine structure. It is the difference between throwing a tennis ball at a parked car and driving 2 cars into each other at matching speed, though perhaps with considerably more regulation and paperwork. These machines became the great engines of modern particle physics. They accelerated protons, electrons, positrons, and other particles to immense energies, and then brought them into collision inside detectors the size of buildings. Those detectors are masterpieces of engineering. They do not see particles the way eyes see objects. Instead, they record tracks, energy deposits, ionization patterns, timing signals, and the signatures left when particles interact with different detector layers. From those traces, physicists reconstruct what happened in the tiny instant of collision. That reconstruction is a serious piece of work. A particle collision is not a neat little snapshot. It is an event with many outgoing fragments, some stable, some short-lived, some neutral, some charged, some escaping undetected. To read a detector event is to infer the invisible from the visible, rather like reconstructing an entire argument from the sound of a slammed door, a broken plate, and somebody quietly saying that was not ideal. The difference, of course, is that in particle physics the inference is done with careful statistics, calibration, and theory rather than household intuition. One of the most striking signatures of quark behavior in colliders is the production of jets. Because quarks cannot escape freely due to confinement, a high-energy quark produced in a collision does not simply fly out and arrive at the detector as a lone quark. Instead, as it moves away, the energy in the strong interaction field grows until new quark and antiquark pairs are produced, leading to a cascade of hadrons moving in roughly the same direction. What the detector sees is a jet, a narrow spray of particles that betrays the presence of an underlying quark or gluon. Gluons can produce jets as well, though with somewhat different characteristics. So even here, where we are trying to see hidden constituents, nature insists on translating them back into colour, neutral visible outcomes, before they reach us. This is a lovely example of how particle physics works. We never catch the quark strolling naked into the detector. Instead, we infer the quark from the jet pattern it leaves behind. The evidence is indirect in one sense, yet overwhelming in another. Quark behavior shapes the event structure so clearly that the theory and the data lock together with remarkable strength. Science is full of this kind of indirect seeing, where the thing itself remains inaccessible in one form, but its consequences become unmistakable. There is also a deeper emotional texture to these experiments that is easy to miss beneath the machinery. We smash matter to see what hides within, because at small scales, matter does not volunteer its structure. The visible world is too calm. A proton sitting in a hydrogen nucleus does not advertise the quark and gluon drama within it. It behaves like a stable little unit. To reveal the inner story, we have to create conditions far removed from daily life. We have to recreate in a controlled way something of the intensity that existed in the early universe. Only then do the smaller patterns become accessible. In that sense, particle accelerators are not just instruments, they are historical machines. They do not merely inspect matter as it is now, they briefly push matter into conditions more like those of the young universe, when energies were high, particles were colliding constantly, and the distinctions we now take for granted were not yet settled into their present calm forms. The deeper we probe, the more the modern laboratory starts to resemble a tiny reenactment of cosmic youth, though thankfully with fewer existential consequences for the nearby furniture. This connection to the early universe becomes even more apparent in heavy ion collisions, where entire atomic nuclei are smashed together at tremendous energies. Under these conditions, physicists can create a state called quark-gluon plasma, in which quarks and gluons are no longer confined into individual protons and neutrons in the ordinary way. For a very brief moment, matter becomes a hot, dense medium, more like what is thought to have existed shortly after the Big Bang. This does not reveal isolated quarks sitting quietly in a row, but it does show that the familiar hadronic structure can melt under extreme conditions. Once again, smashing matter teaches us not only what things are made of, but how stable structures depend on the conditions under which they live. And yet, even with all this smashing, there are limits. Collisions do not simply answer every question on command. They produce data that must be interpreted. They require theory to tell us what patterns to expect from different possibilities. They require enormous care to distinguish signal from background, and sometimes they reveal something frustratingly absent, which is itself a result. If we collide particles at higher and higher energies and still do not see signs of quark substructure, that absence tells us something important. It tells us that if quarks do have an inside, it lies beyond the scale we have reached so far. This is one of the hardest disciplines in science, learning to treat absence not as failure but as information. The collider does not say, "I found nothing, how embarrassing." It says, within this energy range and this resolution, no evidence of compositeness. That moves the frontier. It narrows the space in which deeper theories can hide. It forces speculation to become more disciplined. In that way, even a non-discovery at a collider is often a real discovery about what nature does not appear to be doing. Still, particle collisions have already changed our understanding of matter almost beyond recognition. They revealed that protons and neutrons are not elementary. They showed that quarks behave like point-like constituents at high energy. They helped establish the role of gluons in the Parton picture. They exposed jets, confirmed asymptotic freedom, and deepened the case for quantum chromodynamics as the correct theory of the strong interaction. They also made clear that the proton is crowded inside with momentum and activity distributed far beyond the naive three-quark picture. All of that came from smashing. Not random smashing, but careful, repeatable, instrumented, mathematically interpreted smashing. It is an oddly human method when you think about it. Faced with a reality too small to see directly, we built giant machines, accelerated tiny particles to absurd speeds, and waited for matter to confess through the way it broke apart. There is something both comic and magnificent about that. It is as though the species looked at the hidden structure of the world and said, "Very well then, if you will not open, we shall knock harder." And yet the more successful that method became, the stranger the remaining questions grew. The collisions did not simply reveal neat little components sitting quietly in place. They revealed that energy and matter blur into one another at high enough intensity that gluons carry much of the proton momentum, that temporary quark and antiquark pairs matter, and that even what we call empty space may not be especially empty in the old simple sense, which is where the next layer of the story begins to press forward. Because once high-energy experiments teach you that collisions can pull new particles out of the energy stored in fields and interactions, you start to realize that the space around quarks and inside hadrons may be far less vacant than the word empty ever led us to believe. For almost everything we have talked about so far, there has been one stubborn rule in the background. Quarks do not come out alone. They stay confined inside protons, neutrons, and other hadrons, held there by the strong interaction in a way that makes separation extraordinarily difficult. Try to pull them apart, and the force tightens. Push enough energy into the system, and instead of freeing a single quark, you usually end up making new particles. It is one of the strangest and most defining habits in the whole subatomic world. Quarks seem to belong to groups, and the universe appears very firm on that point. But there is an important word in that sentence, and it is the word seem. Because under ordinary conditions, quarks are confined. Under extraordinary conditions, the story changes. This is one of those moments in physics where the rule turns out not to be wrong, but conditional. On the calm scales of everyday matter, quarks remain locked inside hadrons, inside the atomic nuclei in your body, inside the metal frame of a lamp, inside the carbon of paper, and the calcium of bone. Quarks are doing what quarks have done for most of the visible universe as we know it. They are bound into stable combinations. Yet there was a time when the universe itself was so hot and dense that hadrons had not settled into their familiar form. There was a time when the usual boundaries between quarks and gluons had not yet hardened into the particles that now make ordinary matter possible. There was a time when quarks, in a very real sense, roamed more freely. That time was the early universe. It is difficult to overstate how different the early universe was from the quiet world around us tonight. We're used to a cosmos of stars, planets, dust, atoms, chemistry, and cooling space. We're used to temperatures that permit things like oceans, skin, clouds, coffee, and the occasional underwhelming biscuit. The early universe permitted none of those comforts. It was hotter than anything human intuition is built to handle. It was denser, more energetic, and more compressed than the ordinary language of heat really captures. Matter as we know it had not yet taken on its later forms. The familiar particles of daily life had not calmly assembled themselves into the structures that would someday become rocks, lungs, libraries, and weather reports. In those first tiny fractions of a second after the Big Bang, the universe was not a place full of protons and neutrons drifting about as finished products. It was a much harsher environment, one in which energy densities were so extreme that the usual confinement of quarks inside hadrons did not operate in the same way. Instead, physicists believe the cosmos passed through a state called quark-gluon plasma. That name sounds very modern and faintly expensive, like something developed in a laboratory brochure with more confidence than budget restraint. But it refers to a very serious and remarkable phase of matter. In quark-gluon plasma, quarks and gluons are not neatly packaged into individual protons and neutrons. They exist in a hot, dense medium where the normal boundaries of hadrons have effectively melted. This does not mean that each quark becomes a calm little object, wandering independently through empty space, as if enjoying a country stroll. The picture is not that gentle. It is more like a collective fluid of strongly interacting quarks and gluons, in which the usual hadronic identities are not yet fixed in the familiar way. The phrase roam free is useful, but only if taken with care. Free here means not confined into ordinary hadrons. It does not mean detached from all interaction. In fact, the medium is intensely interactive. The quarks are less imprisoned by individual proton and neutron walls, but they are hardly on holiday. This is one of the important subtleties in the subject. Popular explanations sometimes make it sound as though the early universe was full of quarks cheerfully flying about on their own. The truth is more interesting and less cartoonish. Quark-gluon plasma behaves less like a gas of isolated particles and more like a strongly coupled fluid. That was one of the surprising results when physicists began producing tiny droplets of this state in modern collider experiments. They did not find something simple and thin and weakly interacting. They found something remarkably collective, almost liquid-like in its behaviour, flowing with very low viscosity. In other words, when quarks roam free, they still do so in a world of intense company. That matters because it reminds us that the strong interaction never stops being strong just because the rules of confinement change under extreme conditions. The same basic theory still governs the behaviour. It is just that at sufficiently high temperature and density, the usual bound states melt into a different phase. This is a bit like saying ice and water obey the same deeper chemistry, while behaving very differently depending on temperature. One should not push that analogy too far, because quark-gluon plasma is not merely warm proton juice, and I would advise against describing it that way at any serious dinner. But the general point holds. Matter has phases, and under extreme conditions the phase of strongly interacting matter changes. There is something wonderfully humbling about this. The stable protons and neutrons we take for granted are not eternal default settings built into the universe from the first instant. They are the cooled outcome of earlier conditions. The ordinary matter around us is what strong interaction physics looks like after the universe has expanded and cooled enough for hadrons to form and remain stable. Before that, the world was more fluid, more compressed, and less settled into the particle identities that now feel so basic. One could say that the proton is a kind of late arrangement. It is not a primitive starting point of all time, but a durable product of a universe that had already calmed down from its hotter youth. That is worth sitting with for a moment. The particles that anchor atoms and everything built from atoms are themselves descendants of an earlier phase, where their separate existence was not yet established. The visible world is, in that sense, what happened after the quark-gluon storm cooled enough to organise itself. Now, how do we know any of this? Once again, because physics is rarely handed its answers in tidy boxes, the answer comes partly from theory and partly from experiments designed to recreate, very briefly and in tiny regions, the sort of conditions that existed in the early universe. If you cannot travel back to the first microseconds of cosmic history, the next best thing is to mimic some of their conditions in a controlled way on Earth. This is one of those sentences that sounds absurd until you remember that particle physicists have a long history of making absurd things work through a combination of engineering, stubbornness, and very large magnets. In heavy ion collisions, physicists accelerate large atomic nuclei, often nuclei of gold or lead, to extraordinary speeds and then smash them together. These are not gentle impacts. They produce such extreme temperatures and energy densities in the collision region that, for a fleeting moment, the resulting matter behaves like quark-gluon plasma. The hadrons melt. The quarks and gluons move in a collective medium. Then, almost immediately, the system cools and expands, and the quarks become confined again into ordinary particles that fly outward toward the detectors. The detector does not see a bottle labelled Early Universe Sample. It sees the aftermath. It sees particle tracks, momentum distributions, correlations, energy flows, and signs of collective motion. From these clues, physicists infer that a tiny droplet of quark-gluon plasma was formed. This is very much in keeping with the general style of particle physics. The thing itself is too brief and too small to observe in a naive visual sense, but its fingerprints are all over the event if you know how to read them. One of the most compelling pieces of evidence came from the way the debris from these collisions flowed. Instead of behaving like a thin gas of almost non-interacting particles, the medium expanded in patterns that suggested strong collective behaviour. almost as if it were a liquid with extremely low resistance to flow. This was not what many people expected early on. The phrase quark-gluon plasma had sometimes encouraged the image of something diffuse and weakly coupled. Instead, nature delivered a strongly interacting fluid, a reminder that even when quarks are no longer trapped in individual hadrons, they are still in a deeply social mood. There is a faintly comic quality to that outcome. One might have hoped that if quarks finally escaped their hadronic homes, they would become straightforward and easy to understand. Instead, they emerged into a communal state with new complexities of their own. The universe, as ever, refuses to exchange one mystery for a neat solution, when it can provide a richer problem instead. Still, the existence of quark-gluon plasma tells us something profound about confinement. It tells us confinement is not an absolute metaphysical decree. It is a phase-dependent phenomenon. Under the conditions of ordinary matter, quarks are confined. Under sufficiently extreme conditions, matter crosses into a different phase, where that confinement is no longer expressed through stable individual hadrons. This is a more mature and satisfying picture than simply saying quarks can never be free. They can, in a limited and highly collective sense, exist outside ordinary hadron boundaries. They just require a universe hot and dense enough to make that possible, or a laboratory willing to impersonate one for a fraction of a second. That connects the smallest scales to the largest in a particularly beautiful way. The internal life of the proton is not just a niche matter for particle specialists with impressive computing budgets. It's tied directly to cosmic history. To understand what a proton is now, you benefit from knowing what matter was like before protons had settled into existence. To understand quark confinement, you benefit from knowing the conditions under which confinement breaks down. The early universe is not separate from the particle story. It is part of the same narrative, only earlier and much less hospitable. It also changes the emotional feel of the topic. We began with the quiet question of what happens inside a quark. Then we found that the proton itself was crowded, that gluons mattered enormously, that C-quarks flickered in and out, and that quarks were confined by a force that grows more stubborn when separation is attempted. Now we discover that the confinement rule itself depends on the thermal history of the universe. The deeper we go, the less the world resembles a stack of solid little bits, and the more it resembles a set of conditions under which different forms of matter become possible. That is a very modern way of seeing nature. Things are not merely what they are in isolation, they're also what their environment permits them to be. Water is not always liquid, carbon is not always diamond or graphite. Matter made of quarks is not always protons and neutrons. At different temperatures and densities, the same fundamental ingredients organize themselves differently. The universe has a phase history, and ordinary matter is only one chapter of it. There is something quietly soothing in that, oddly enough. The stable world around us is not fragile in the everyday sense, but it is contingent. It emerged from cooling, expansion, and a long sequence of changing conditions. Your hand resting on a blanket, the wooden frame of a chair, the calcium in a tooth, all of it depends on a cosmos that once ran so hot no proton could yet hold itself together in the form we now take for granted. Stability is not the beginning of the story. It is the outcome. This is one reason cosmology and particle physics belong together more closely than they sometimes appear to from the outside. The largest structure of the universe and the smallest constituents of matter are not separate hobbies pursued by scientists who merely happen to share a canteen. The early universe was a particle physics environment. Its temperatures and densities determined which particles could exist, which symmetries were broken, which forms of matter became stable, and how the later visible universe took shape. To ask about quarks is already, whether one meant to or not, to ask about the first moments of cosmic history. And even now, in the present universe, nature preserves a faint memory of those conditions in places more extreme than daily life. In the cause of certain violent astrophysical environments, in the aftermath of heavy ion collisions, and in the theory that links these states to the earliest moments after the Big Bang, we see reminders that the usual hadronic world is not the only possible arrangement of quarks and gluons. There are other phases waiting at the edges of temperature and density, where matter reorganizes itself under pressure like an empire changing governments. That may sound grand for something so brief and microscopic, but quark-gluon plasma really is a glimpse behind the curtain of ordinary matter. It shows us what the strong interaction can do before it settles into the protons and neutrons that later populate atomic nuclei. It lets us study, in miniature and for an instant, a state of matter that once filled the whole universe. Few scientific achievements feel more audacious than that. We built machines on one small planet, hurled nuclei into one another, and from the resulting spray learned something about the thermal character of the cosmos when it was younger than a heartbeat. And yet, the story does not end with quarks briefly roaming more freely. In a way, that result sharpens the next question rather than answering it. If quarks can be confined in one phase and comparatively deconfined in another, if protons and neutrons are not eternal primitives but cooled products of a hotter state, then it becomes natural to wonder whether our current picture of quarks as elementary is itself another phase of understanding rather than a final flaw. Perhaps quarks are truly fundamental, perhaps they are not. But either way, the lesson of the early universe is that what looks permanent at one scale or condition may turn out to be only the calm arrangement that survives after deeper violence has cooled. By this point, the story has become pleasantly inconvenient. We began with the ordinary instinct to look inside things, and that instinct seemed perfectly sensible. Atoms had structure, nuclei had structure, protons and neutrons had structure. Quarks, then, felt like the next obvious target. Surely they too must contain something smaller, tucked away behind the current limits of our machines. And then the subject started resisting us in a deeper way, not just by hiding the answer, but by making us question the shape of the question itself. That resistance becomes strongest when quantum physics enters fully into the picture, because quantum physics has a habit of taking the clear, comfortable edges of everyday intuition and softening them until they no longer behave like edges at all. In ordinary life, structure usually means parts arranged in space. A house has rooms, a watch has gears, a loaf has crust and middle. You can point to the boundary, cut into the object, and reveal the arrangement within. Even when the object is complicated, the basic logic remains intact. There is an outside, there is an inside, and the interesting work of understanding consists in moving from one to the other. But a great deal of the subatomic world does not cooperate with that picture. It has structure, certainly, but not always structure with edges in the familiar sense. A proton has internal organization, but its quarks do not sit inside it like pebbles in a pouch. Their positions are not fixed in the ordinary way. Their behavior is described by quantum states, by distributions, by interactions, by fields, by probabilities. Even the boundary of the proton is not like the boundary of a marble. It is not a hard surface you could scrape with a smaller fingernail if only you had one. It is more like a region in which certain interactions and probabilities matter more strongly, a physical structure that is real without being neatly outlined. And if that is true even of the proton, which does have internal complexity, then it becomes even more important when we talk about quarks, which as far as we can currently tell do not have smaller parts inside them. A quark may have physical properties, measurable effects, and a central role in the architecture of matter, but none of that requires it to possess an inside in the old geometric sense. It may be structureless in the sense that there are no smaller constituents to uncover, while still being rich in the quantum sense, meaning that it is defined by its behavior, its charges, its mass, its spin, and its participation in the fields of the theory. This is one of the hardest transitions the mind has to make in modern physics. We are extremely good at imagining little objects. We are less good at imagining that an object can be physically real and deeply consequential without having a little surface and a little interior that mirror the things we know from ordinary scale. Yet this may be exactly what nature is asking us to accept. The subatomic world seems to have organization without miniature furniture. It seems to have entities whose reality comes not from having tiny visible anatomy, but from how they behave under the rules of quantum fields. The word field can sound discouragingly abstract when it arrives too quickly, but it is worth lingering over because it is one of the keys to this whole mystery. In modern physics, a particle is not usually treated as a tiny independent pellet moving through a void. Instead, the more basic description involves fields spread throughout space, with particles appearing as excitations of those fields. An electron is an excitation of the electron field. A quark is an excitation of a quark field. A photon is an excitation of the electromagnetic field. Gluons belong to their own field as well. What we call a particle is, in this picture, a localized quantum event within a broader field structure. That is already a strange way to describe the world if your mental training came mostly from kitchen drawers and raincoats. It means the classical image of little balls drifting about in empty space is not the deepest available account. It can be useful in some situations, much as a cartoon map can help you find the train station, but it is not the full story. The deeper description replaces tiny solid lumps with excitations, interactions, and probabilities. In other words, matter becomes less like a pile of miniature stones and more like a pattern of stable notes being played on invisible instruments. That image too should be handled gently, because every analogy eventually gets tired and sits down. Still, it helps to make one point clear. A note in music is real. It has effects. It can carry information and structure. Yet it is not made of smaller notes tucked inside it. It is a mode, a pattern, a vibration of something more fundamental. In a rough and very limited way, quantum particles are rather like that. They are not meaningless abstractions. They are physically real manifestations of fields. But asking for the inside of one may be like asking for the inside of a musical note. One can ask what produces it, what rules it follows, how it interacts, how stable it is, how it contributes to larger structures. Yet one may be asking the wrong sort of thing if one imagines a hard shell with tiny parts rattling around inside. This does not mean the world becomes vague or unreal. Quite the opposite. Quantum theory is astonishingly precise in what it predicts. The trouble lies not in reality itself, but in the mismatch between reality and the visual habits we inherited from medium-sized life. We like crisp outlines because the macroscopic world trains us to trust them. Chairs have edges. Doors have edges. Biscuit tins have edges, though what happens to the contents over time remains one of the great unsolved domestic problems. But subatomic entities are not obliged to present themselves in the same way. Their properties are real, yet their reality is not always organized around boundaries that look familiar. Consider how even the location of a particle is handled in quantum mechanics. In the classical picture, an object has a definite position and momentum at the same time, even if we happen not to know them. In the quantum picture, those quantities are not simultaneously fixed in that old straightforward way. A particle is described by a quantum state that gives probabilities for different outcomes when measured. This does not mean the particle is imaginary, or that physics has become indecisive. It means the world at that scale is not built to match our old expectations of little objects tracing neat paths with permanent private addresses. So when people picture a quark inside a proton, sitting at a definite little coordinate as if waiting for a bus, that picture must be treated with caution. The quark is real, the proton is real, the interactions are real. But the best description is not that of tiny marbles inside a tiny bag. The interior structure of the proton is quantum structure. It is described through distributions and interactions, and if quarks themselves are elementary, then the same caution becomes even more essential. The quark does not need an edge to be real. It does not need a miniature inner cavity to have properties. It can be a genuine physical constituent without being a little object in the old mechanical sense. This is where the phrase structure without edges earns its keep. The proton has structure without sharp boundaries in the everyday sense. A quark, if elementary, may have properties without internal structure. A quantum field has organization without being an object in the ordinary material sense at all. We are moving into a realm where the old language of containers, shells, surfaces, and hidden bits begins to lose its authority. The mystery is not just that the world is small. The mystery is that smallness changes what structure itself means. One of the reasons this can feel so unsatisfying at first is that decomposition has served science extremely well. We learned about chemistry by breaking compounds into elements. We learned about atoms by probing them into nuclei and electrons. We learned about nuclei by finding protons and neutrons, and then learned about those by inferring quarks. It is tempting to assume that every successful layer of science will always lead to another smaller layer underneath, waiting to be opened like the next box in a nested set. But quantum theory warns us that the deeper pattern may not always be another box. Sometimes it may be a change in description rather than another object. That is a subtle idea, but it shows up all across modern physics. Take temperature. At one level, temperature is a useful physical quantity. At a deeper level, it is not a thing with its own little internal organs. It is a summary of collective microscopic behaviour. Similarly, what looks like a separate object at one scale may, at a deeper scale, turn into a pattern of relations and excitations, rather than a smaller chunk of stuff. The closer physics gets to the foundations, the more it has to loosen its reliance on the intuition that everything is just another object made of still smaller objects. This also helps explain why particle physics leans so heavily on experiments involving scattering. If you cannot talk meaningfully about a tiny visible surface, then the way to study a particle is through how it interacts. You learn what it is not by looking at its miniature appearance under a lamp, but by seeing how it responds when probed, what charges it carries, what conservation rules it obeys, what products emerge in collisions, what symmetries shape its behaviour. In the quantum world, interaction is often more revealing than appearance. Perhaps that is true of human beings too, though usually with less elaborate machinery. It is also worth noticing that the lack of sharp edges does not imply lack of size in every practical sense. A proton has an effective size, meaning there is a scale over which its charge and internal structure are distributed. Yet this size is not the size of a hard sphere. It is not a shell you could knock on. It is a measure derived from the way the proton behaves in experiments, from how its internal contents are distributed, and how it responds to probes. In the same way, when quarks are treated as point-like, that does not mean they are little mathematical dots floating through a childlike cartoon of empty space. It means that no internal extension or substructure has shown itself in the experiments that probe them. This distinction between measurable behaviour and visual metaphor is one of the deepest disciplines in the subject. The mind always wants a picture. Physics often gives a pattern instead, and the pattern, though less comforting to imagination, is usually far more faithful to reality. There is another reason the edges blur at small scales, and it has to do with the role of the vacuum. In ordinary speech, empty space sounds like nothing. In quantum theory, empty space is not really nothing in that old blunt way. Fields are present, fluctuations are possible. Virtual processes contribute to the behaviour of particles and interactions. Even the proton interior, which might once have been imagined as 3 quarks and a lot of blank room, turns out to be full of gluonic activity and C-quarks. The closer one looks, the less the old notion of empty space survives unchanged. That makes the idea of a clean, isolated object harder to sustain. A quark is not simply a tiny nugget detached from a dead background. It exists within a world of fields and interactions that are always there. Its properties are shaped by that context. Even the mass and charge we assign to fundamental particles are understood within the broader framework of quantum fields and the ways those fields behave. Once again, reality becomes more relational than object-based. The quark is not less real for that. It is simply less like a pebble than our ancestors would have preferred. And perhaps this is why the question of what is deeper than a quark continues to tug at people, even when the current evidence says quarks are elementary. We're not merely asking for smaller parts. We're asking whether there is a more satisfying kind of picture, some way to regain the comfort of structure that can be visualized. But the answer may not be a better picture. It may be a better grammar. We may have to give up the demand that every level of nature look like a smaller version of the one above it. Quantum theory has already taught us this lesson in several ways. Light is both particle-like and wave-like depending on how it is probed. Electrons do not orbit nuclei the way planets orbit stars. Empty space is not truly empty. Measurement is not just passive observation. Particles are excitations of fields rather than tiny classical pellets. Once one has accepted all that, the idea of structure without edges becomes less absurd and more like the natural next step in a long process of intellectual house training. Physics keeps removing the cushions from our common sense until we either become more careful or sit on the floor. Still, one should be honest about how unsettling this is. It is not easy to replace the old visual world with a quantum one. The old visual world gave us satisfying narratives. Things had parts, and parts had smaller parts, and eventually one would arrive at the smallest pea in the pod. The quantum world gives us entities that may be fundamental, fields that cannot be pictured as ordinary stuff, and structure that is encoded in mathematics and interaction, rather than in miniature mechanical interiors. It asks us to accept that reality may be more exact than our imagination, not less. That exactness is important. The theory is not simply saying anything goes, quite the opposite. The standard model is tightly constrained. Quarks come in specific flavors. They carry particular charges. They interact through the strong force according to strict rules of color charge and gluon exchange. The fact that these things are difficult to picture does not make them vague. It only makes them non-classical. The mathematics is firm even when the mental imagery stumbles. And that brings us to a quieter philosophical point. When people ask whether a quark has an inside, they are often asking about the nature of explanation itself. What counts as understanding? Is it enough to know the properties and interactions of a thing, or do we only feel satisfied if we can reduce it to smaller pieces? Physics may be telling us that these are not always the same demand. There may come a stage where understanding no longer means taking apart, but seeing how a supposedly basic entity fits into the network of rules from which the world is built. That is not a retreat from depth, it is a different kind of depth. Instead of asking what smaller things a quark contains, one asks why quarks have the masses and charges they do, why there are several flavors, why the standard model takes the form it does, whether those patterns point to a deeper symmetry, and whether what looks fundamental now will remain fundamental under future experiments. These are not shallower questions than the question of hidden interior. In many ways they are deeper, because they ask not for more objects but for more principle. So the quantum mystery here is not just that the small world is hard to see, it is that the small world may not be built from edges in the way our ordinary lives trained us to expect. Matter may have organization without miniature shells. Particles may have reality without internal anatomy. Fields may underlie what we call objects, and the deeper structure may be found not by slicing into things, but by uncovering the rules that make the things possible at all. Once that possibility settles in, the original question changes its tone. What happens inside a quark may no longer sound like a request for a tiny autopsy. It begins to sound like a question about whether depth in physics must always mean smaller pieces, or whether sometimes it means better descriptions, stronger symmetries, and a more honest acceptance that the universe is under no obligation to provide the sort of edges we find comforting. By now the question has changed its shape more than once. We began with it in the most natural way possible, with the ordinary human habit of opening things. We open boxes, books, clocks, cupboards, seed pods, and now and then an email we should probably have ignored. We trust by long habit that if something exists, then there may be a smaller arrangement tucked inside it waiting to be uncovered. That instinct has served physics remarkably well. It took us from molecules to atoms to nuclei, from nuclei to protons and neutrons, and from those to quarks. At each stage, the world turned out to contain one more layer than the previous generation had confidently expected. It is no wonder, then, that we turn to quarks and ask the same old question once again. Very well, then, what happens inside one of those? And after all this wandering through protons, gluons, confinement, collisions, quantum fields, and the early universe, the answer turns out to be both simpler and stranger than the question first promised. According to the best evidence we have, nothing happens inside a quark in the ordinary compositional sense, because a quark does not appear to have an inside of that kind. It does not seem to be a tiny container full of smaller ingredients. It does not behave like a miniature machine with hidden parts. It does not present any confirmed sign of substructure in the experiments we have been able to perform. As far as modern physics can presently tell, the quark is elementary. That is the direct answer, and like many direct answers in science, it sounds almost disappointingly short after such a long journey, but only almost. Because the moment you say it aloud, the real meaning begins to spread outward. If nothing happens inside a quark in the old familiar sense, then a great many things must be reconsidered. What counts as structure? What counts as explanation? What counts as the deepest level of reality? And perhaps most importantly, what kind of creatures we are, that we keep expecting the universe to look like a smaller version of the world we already know. The ordinary mind, which is a splendid tool in most matters involving cooking, walking, and not stepping into ponds by accident, tends to imagine reality as a stack of objects. A loaf is made of slices. A watch is made of gears. A chair is made of parts. So the atom must be made of smaller parts, and those of smaller parts still, until finally one reaches the last hard little bead at the bottom. That is a very understandable way to think, because the middle-sized world really does contain a great many nested objects. But physics, at its deepest known levels, begins to suggest that this nesting instinct is only partly right. There are layers, yes, but the layers do not go on forever in the same style. At some point, the deeper description stops looking like smaller furniture and starts looking like properties, symmetries, and fields. That can feel unsettling at first because it denies us the comfort of miniature mechanics. We would like the quark to be a tiny version of a familiar thing. We would like it to have edges, contents, perhaps a few polite internal workings that click into place under close inspection. Instead, what we get is an entity with measurable properties, definite roles, and extraordinary physical importance, but no observed internal anatomy. The quark is real, but not in the toy model sense our imagination keeps trying to force upon it. And yet, it would be a mistake to think this makes the quark dull or empty. Quite the opposite. A quark may not contain smaller known parts, but it participates in some of the richest physics in the universe. It carries electric charge, it carries color charge, it has spin, it belongs to a flavor family. It interacts through the strong force, can change flavor through the weak force, and helps build the protons and neutrons that make atomic nuclei possible. A quark may not have an inside, but it has a life, if one may use the term loosely enough, and that life is deeply bound up with the structure of matter. This is perhaps the most important shift in the whole story. At the deepest level we currently know, being may matter more than containing. A thing does not have to hide smaller objects in order to be physically rich. It can be fundamental and still be full of consequence. The old intuition says that significance comes from what something is made of. Modern physics replies that significance can also come from how something behaves, what properties it carries, and how it fits into the wider pattern of the world. That wider pattern is worth pausing over, because it is rather beautiful when seen as a whole. Quarks help form protons and neutrons. Those help form nuclei. Nuclei and electrons form atoms. Atoms form molecules. Molecules form materials, cells, breath, bone, bark, rain, salt, bread, ocean spray, and the paper of old books. A quark, then, may have no inside, yet it sits near the root of almost everything you can touch. The visible world rests partly on entities that may be irreducible in the ordinary compositional sense. That is a stunning thought. The universe may not be built all the way down from smaller and smaller chunks of familiar kind, but from a small set of elementary actors whose interactions generate everything else. There is something deeply instructive in that. It suggests that reality is not obliged to satisfy our appetite for endless nesting. The mind loves the promise that every answer will contain another smaller question shaped exactly the same way. Physics has shown us that many times this is true for a while, and then suddenly it may not be. The proton contains quarks. The quark, as far as we know, does not contain tinier protonlets or subquarks or some bustling micro-village of components waiting to be discovered. If there is a deeper layer, it has stayed hidden beyond every confirmed test so far. That may change one day. Science does not close its books with a theatrical snap, but for now reality seems comfortable with the possibility that some ingredients are simply fundamental in the present description. And if that is so, then the question of what happens inside a quark transforms into a different question altogether. Not what smaller parts does it hide, but what does its apparent simplicity tell us about the world? The answer may be that the world is less object-based and more relational than our daily intuition ever suspected. Quarks do not mean much in isolation from the framework around them. Their identities are tied to fields, to interactions, to symmetry rules, to confinement, to the strong force, to the electro-weak structure of the standard model. In other words, what a quark is cannot be separated cleanly from what a quark does. That is a very modern sort of truth. We tend to think of objects first and relations second. Physics increasingly suggests that, at deep levels, the relations may be just as fundamental as the objects. A proton is not merely three quarks sitting in a box. It is a bound state sustained by gluons, C-quarks, and constant quantum activity. A quark is not a tiny pebble. It is an excitation of a field carrying a particular bundle of properties. The deeper the story goes, the harder it becomes to keep drawing a line between a thing and the rules by which it exists. This also tells us something about knowledge itself. Human beings are fond of the kind of understanding that comes from taking things apart. There is good reason for that. It works beautifully in much of science and much of life. But perhaps there are limits to that kind of understanding. Perhaps some truths are not reached by opening a box and removing the contents, but by recognizing that the box was never the right metaphor in the first place. To understand a quark may not require a smaller interior. It may require a more honest grammar, and this, quietly, is one of the most philosophical moments in all of physics. We usually imagine that depth means smaller pieces, but depth might also mean more exact principles. It might mean better symmetries, more fundamental laws, cleaner mathematical relations, deeper patterns of field behavior. If quarks are truly elementary, then the final step downward may not be a further object, but a further rule. Not another bead at the bottom of the necklace, but a better account of why the necklace exists at all. One can already see hints of that in the standard model. The theory is tremendously successful, yet it leaves open questions that do not sound like old-fashioned taking apart questions. Why do the quark masses take the values they do? Why are there several generations of particles? Why do the different forces have the structure they do? Why is the standard model what it is and not some other arrangement? Those are not questions about what is inside a quark. They are questions about the architecture of the whole framework, and that may be where the next level of depth really lives. It is entirely possible, of course, that future physics will yet reveal some deeper compositeness. Perhaps quarks are not truly elementary after all. Perhaps at energies far beyond our current reach, they will begin to show excited states or internal structure. Perhaps the standard model itself is only an effective description of something still deeper. Physics would not be embarrassed by that. It has survived such revisions before, but even if that day comes, the lesson of the quark will remain valuable. It will remind us that the universe does not reveal new layers just because we want them. It reveals them when evidence compels it. That discipline is part of what makes science trustworthy. It is not merely a factory for clever possibilities. It is a method for learning which possibilities survive contact with the world. For the moment, the world keeps telling us that quarks behave as structureless particles down to the scales we have tested. So the responsible answer to our original question is not a flamboyant guess about tiny things inside tiny things. It is a measured statement, As far as we can tell, nothing happens inside a quark because the quark does not appear to be composite. What happens instead is around it, through it, because of it, and among quarks and gluons in the larger structure's matter builds. There is something curiously satisfying about that once the initial disappointment passes. The question that sounded like it would lead to one more hidden compartment instead leads to a clearer view of what reality may be like at the bottom of our present knowledge. Not a museum of smaller and smaller mechanical bits, but a world of elementary ingredients defined by fields and interactions. Not a final crumb inside the loaf, but a limit to the loaf metaphor altogether. And that says something rather profound about us as well. We are creatures of surfaces. We live among doors, fruit, weather and fabric. We built our language on visible objects, and our common sense on medium-sized events. Of course we expect the universe to keep behaving that way at every scale. Of course we want the quark to have an inside, because that would let us keep using the same mental habits all the way down. But the universe seems under no obligation to remain comfortable merely because comfort is familiar. That is one of the reasons physics can feel at once humbling and oddly intimate. It takes the world out of our preferred categories, yet in doing so it gives us a more truthful place within it. We are not outside nature looking in. We are arrangements made possible by the same deep rules we are trying to understand. The atoms in your body contain protons and neutrons. Those contain quarks. The strong force binds them. The masses of ordinary things depend heavily on the restless energy inside those bound states. Your very material existence rests partly on a question that ends, for now, with the possibility that its deepest ingredient has no further inside to inspect. There is a certain peace in that, though one has to arrive at it slowly. The world does not become less wondrous because the chain of hidden interiors may pause with the quark. If anything, it becomes more wondrous, because it suggests that simplicity and richness can coexist. A fundamental particle may be elementary and yet help generate a universe of staggering complexity. A tiny ingredient may have no smaller pieces and yet stand at the beginning of stars, blood, paper, breath, and the warm fatigue that settles over a person at the end of the day. So what happens inside a quark? Probably nothing in the ordinary sense. No gears, no grains, no hidden drawers, no smaller actors waiting nervously backstage. What happens instead is that the quark exists as one of the current elementary ingredients of the physical world, carrying its properties, obeying its rules, participating in the strong force, helping to build the proton and neutron, helping to build the nucleus, helping to build the atom, helping to build nearly everything you know. And what does that say about reality? It says that reality may not be made of endlessly smaller versions of familiar things. It says that at some point explanation may shift from taking apart to understanding relations. It says that the world is under no duty to satisfy the visual habits of creatures who evolved to judge distance by throwing stones and timing, the run to shelter before the rain. It says that the deepest truth may look less like a tiny machine and more like a set of stable patterns woven through fields and forces. Most of all, perhaps, it says that mystery does not disappear when a question is answered well. It changes form. We asked what happens inside a quark, and the best answer led us not to one more hidden chamber, but to the edge of our present understanding, where the nature of matter starts to blur into the nature of law itself. That is not the sort of answer one can hold in the hand, but it may be the sort worth carrying in the mind. And now, after all this time spent among protons and plasmas, confinement and collisions, fields and the strange calm of elementary things, here you are again in your own little corner of the universe, made of the very matter we have been talking about, though hopefully in a rather more organised fashion than the early cosmos managed. Somewhere around you the room is quiet. Somewhere inside you, ancient particles are doing exactly what they have always done, with no concern at all for whether we find them intuitive. So before sleep catches up, let me ask you once more, gently, what time is it where you are right now, and where in the world are you listening from tonight? It is funny, really. After all this talk of whether time is fundamental, whether quarks have an inside, whether matter once flowed in hotter, stranger forms, we still return to these small human anchors. A room, an hour, a voice, a question, a mind slowly loosening its grip on the day. And if this quiet journey through the deep structure of things gave you a little calm, or a little wonder, or simply a softer road into rest, I would be grateful if you liked the video, perhaps subscribed, and joined me again for another slow wander through the universe. Science can be loud in places, certainly. It can collide particles, break apart assumptions, and leave us staring at the ceiling in thoughtful confusion. But every now and then it also offers something gentler, the reminder that beneath all the noise of the day there is a deeper order, strange and subtle and endlessly patient, carrying on whether we notice it or not. Sleep well then, wherever you are. The quarks, such as they are, will keep their counsel. The gluons will continue their tireless work. And the world, built from these quiet mysteries, will go on being far stranger and far more beautiful than it first appears,